Imagine an explosion so powerful it outshines entire galaxies for weeks. A cosmic blast that can tell us stories about the universe's deepest secrets. Now, what if I told you some of these explosions, supernovae, don't behave the way we expect? Some don't leave behind the usual cosmic dust, those tiny particles that usually form when stars die in these spectacular blasts. These are called dust-free supernovae, and they're puzzling astronomers in ways that might change how we understand the cosmos. But before we continue, subscribe to the channel so you don't miss out on any of these videos. Supernovae are among the most dramatic events in space. When massive stars run out of fuel, they collapse and explode, spewing out elements that become the building blocks for planets, life, and everything around us. Normally, these explosions produce a huge amount of dust, microscopic solid particles made of elements like carbon, silicon, and oxygen. This dust drifts through space, helping new stars and planets form. But dust-free supernovae are the oddballs. They don't produce much dust, or sometimes any at all. Why? That question has astronomers scratching their heads and digging deeper into the physics of these cosmic events. To understand why this is such a big deal, you need to know how important dust is. Cosmic dust acts like a cosmic seed. Without it, new stars and planets can't form easily. Dust also shapes the light we see from space. When dust is present, it absorbs and scatters light, changing what telescopes detect and even affecting how we measure distances and the universe's expansion. So, when a supernova suddenly appears dust-free, it disrupts our usual way of reading the universe. Scientists first started noticing dust-free supernovae when some supernova explosions didn't show the expected signs of dust. Usually, when dust forms, it blocks some of the light, causing certain features in the light spectrum to change. But in these strange supernovae, the light stayed clean and clear, as if no dust was formed at all. This was surprising because dust formation is thought to be a natural part of the supernova process. One type of dust-free supernova that has intrigued astronomers is the type Ia supernova. These happen when a white dwarf star in a binary system steals material from its partner star until it hits a critical mass and explodes. Type Ia supernovae are important because they act as standard candles, objects with known brightness used to measure distances in space. Scientists expect these explosions to create dust, but many type Ia supernovae show very little to no dust formation. This raises questions about the environment around the exploding star and the exact mechanisms behind the explosion. Researchers have several ideas about why dust-free supernovae might happen. One thought is that the explosion happens in an environment that's too hot or too energetic for dust grains to form. Dust particles need relatively cool conditions to clump together and survive. If the explosion is too violent, it could destroy any dust before it can settle. Another idea is that the material ejected by the explosion might move too fast, spreading dust particles too thinly to detect or preventing them from clumping into larger grains. There's also a chance that the chemical makeup of the star influences dust formation. Some stars might explode without producing enough of the elements that make up dust, or the explosion might push those elements into a state where they can't form solid grains. This chemical puzzle is part of the larger mystery about how stars evolve and die, and how elements get recycled in the universe. Dust-free supernovae don't just challenge our understanding of star explosions, they also force us to rethink how galaxies evolve. Galaxies grow and change as stars form, die, and seed space with dust and heavy elements. If some supernovae don't produce dust, that could affect how fast new stars form and how the galaxy's chemical makeup changes over time. It might also impact the way we understand the early universe, where dust played a role in cooling gas clouds that formed the first stars and galaxies. This puzzle connects to other big questions in astronomy too. For example, understanding dust formation is crucial for studying black holes and neutron stars left behind by supernovae. Dust can hide these objects or change the signals we get from them. So, if some explosions skip dust, it might mean we need to adjust our methods for spotting and studying these exotic remnants. On a more practical level, dust-free supernovae can impact how we use supernovae as tools for measuring the universe. Since Type I supernovae are used to gauge cosmic distances and help discover dark energy, any surprises in their dust production could tweak our estimates of the universe's size, age, and how it's expanding. This could have ripple effects in cosmology, changing what we think about the universe's fate. Scientists use a range of methods to study dust-free supernovae. Observations across many wavelengths, from visible light to infrared and even radio waves, help detect dust or the lack of it. Infrared light is especially useful because dust glows in infrared as it absorbs energy from the explosion. If there's little infrared emission, it suggests little dust. Telescopes like the Hubble Space Telescope, Spitzer, and now the James Webb Space Telescope give astronomers powerful tools to peer into these explosions and gather data. Computer simulations also play a big role. Scientists model the physics of supernova explosions, trying to recreate the conditions that lead to dust formation or prevent it. These simulations help test ideas about temperature, chemical composition, shockwaves, and how dust grains might form or get destroyed. Comparing these models to real observations helps refine theories and guides future research. Another interesting angle is how dust-free supernovae fit into the broader category of peculiar supernovae. Not all supernovae fit neatly into established types. Some have weird brightness patterns, unusual chemical signatures, or unexpected dust properties. These outliers hint at a diversity in star deaths that we don't fully understand yet. Dust-free supernovae could be one type of these oddball explosions, revealing new physics or star types we haven't studied in depth. Looking forward, ongoing and upcoming surveys and missions promise to uncover more dust-free supernovae and other mysteries. Projects like the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will scan the sky in unprecedented detail, finding thousands of new supernovae every year. With so much data, scientists hope to identify patterns and maybe link dust production to specific star properties or cosmic environments. Understanding dust-free supernovae also touches on the quest to understand life's origins. Dust from supernovae contributes to the mix of elements that eventually make up planets, and even biological molecules. If some explosions don't add dust, it changes the story of how the universe became hospitable for life. This cosmic dust is a piece of the puzzle that connects the Big Bang to you and me. In a way, dust-free supernovae remind us how much we still don't know about the universe. For decades, supernovae were considered well-understood phenomena, but these dustless explosions show there are hidden details and surprises. Each discovery pushes the boundary of human knowledge, making us rethink what we thought was settled science. The story of dust-free supernovae is far from over. As telescopes get better and theories evolve, we might find new types of explosions, new ways dust forms, or even entirely new cosmic processes. Maybe one day, understanding why some supernovae don't produce dust will unlock answers to questions about dark matter, dark energy, or the ultimate fate of the universe. Until then, these silent, dustless blasts continue to light up the cosmos in a strange and beautiful way. They challenge us to look deeper, think harder, and keep exploring the vast unknown beyond our little blue planet. The universe is full of mysteries, and dust-free supernovae are one of the most intriguing among them. A cosmic puzzle that promises to keep scientists busy for decades to come. Now, one thing to understand is that supernovae are not all created equal. They come in different types, mainly Type 1 and Type 2, and each has its own story about dust production. Dust-free supernovae seem to pop up mostly among certain subtypes, which adds another layer to the mystery. Type 2 supernovae, which come from massive stars collapsing at the end of their lives, usually create a lot of dust. The outer layers of the star, rich in heavy elements, get blasted into space and cool down enough for dust grains to form. But with some Type 2 supernovae, astronomers notice almost no dust. This lack of dust could be telling us something about the star's environment before it exploded. Maybe the star lost most of its outer layers due to strong stellar winds or interactions with a nearby star, meaning less material was available to make dust. Or the explosion itself might have been so energetic that it destroyed dust as soon as it started to form. In other words, the process is like trying to bake bread in a furnace too hot. the dough never has a chance to rise. Another fascinating piece of this puzzle comes from studying the remnants left behind after the explosion. When a star goes supernova, it often leaves a neutron star or black hole in its place. These remnants can interact with the expanding cloud of gas and dust, called a supernova remnant. The energy and radiation from these remnants can either help dust survive or destroy it. In dust-free supernovae, maybe the remnant is unusually energetic, wiping out dust before it settles. One particular example that's grabbed attention is the supernova remnant known as Cassiopeia A. It's one of the youngest supernova remnants in our galaxy, about 11,000 light-years away, and astronomers have studied it intensely with many telescopes. Surprisingly, Cassiopeia A shows less dust than expected for its age and type. This discovery made scientists rethink how and when dust forms after a supernova. Maybe dust takes longer to form or needs specific conditions that aren't always met immediately after the explosion. Dust-free supernovae also pose a challenge to our understanding of the early universe. Right after the Big Bang, the universe was mostly hydrogen and helium, with very little dust or heavy elements. The first stars, called population 3 stars, were massive and short-lived, exploding as supernovae and seeding the universe with the first dust and metals. If many early supernovae were dust-free, then the timeline for dust enrichment, and consequently, planet and star formation, might be different than we thought. This possibility has big implications for how we model galaxy formation and evolution. Dust cools gas clouds, helping them collapse and form new stars. Without dust, star formation would be less efficient. So, if dust-free supernovae were common in the early universe, it could mean the first galaxies took longer to form or were different in structure. Scientists are also trying to figure out if the dust-free nature of some supernovae affects the types of elements distributed into space. Since dust grains often carry heavy elements like carbon, oxygen, silicon, and iron, less dust could mean less material for building planets and life. This adds a cosmic twist to the question of why our solar system has the particular mix of elements it does. On the other hand, there's a chance that dust-free supernovae actually spread elements more evenly in gas form, which might influence how those elements mix in the interstellar medium. This could lead to more uniform chemical distributions in some regions of space, which is an interesting idea that scientists are still exploring. When astronomers look for dust in supernovae, they don't just rely on visible light. Infrared observations are key because dust absorbs ultraviolet and visible light and remits it in the infrared. The absence of expected infrared signals is a strong clue that dust isn't forming or is very sparse. Some dust-free supernovae show no infrared glow at all, which has been a big surprise since the physics predicted dust formation as a natural outcome. There's also a debate on whether what we call dust-free supernovae are truly dust-free or if the dust is just hidden from our view. Maybe dust forms in clumps or in layers that are harder to detect. Or perhaps it's made of materials that don't emit or absorb light in the ways we expect, making it nearly invisible. This hidden dust hypothesis is an ongoing area of research. The complexity doesn't end there. Sometimes, the interaction between the supernova ejecta, the material thrown out, and the surrounding gas and dust can create shock waves that destroy existing dust. So, what if a supernova appears dust-free because it blew away or obliterated dust that was already there? This makes it tricky to tell if dust was never formed or just wiped out. Another interesting connection comes from supernovae in different types of galaxies. Dust properties vary widely across galaxies, from dusty starbursts to more dust-poor elliptical galaxies. Dust-free supernovae might be more common in certain galactic environments, helping astronomers understand how local conditions affect star death and dust creation. This also relates to metallicity, the amount of elements heavier than hydrogen and helium present in a star. Lower metallicity stars, which have fewer heavy elements, might produce less dust when they explode. Studying dust-free supernovae across galaxies with different metallicities can reveal how chemical composition influences dust production. As we look to the future, new technologies promise to shed light on this cosmic mystery. The James Webb Space Telescope, JWST, launched recently, is designed to observe the universe in the infrared with unprecedented detail. JWST can detect faint dust emissions in distant supernovae that older telescopes might have missed, potentially rewriting what we know about dust formation in these explosive events. Similarly, the next generation of ground-based telescopes, like the Extremely Large Telescope, ELT, will allow astronomers to analyze supernova spectra in greater detail and from farther away. This means we can study dust-free supernovae not just nearby but across cosmic history, giving clues about how dust production has changed over billions of years. Beyond astronomy, understanding dust-free explosions might have implications for physics too. The process of dust formation involves complex chemistry and solid-state physics under extreme conditions. Dust grains begin as tiny clusters of atoms that must stick together despite intense heat and radiation. Figuring out how these grains form, or fail to, can inform material science and chemistry under extreme environments, fields that impact technology here on Earth. At its core, the mystery of dust-free supernovae invites us to rethink how the universe recycles matter. Stars are like cosmic factories, breaking down and building up elements in cycles that last billions of years. Dust is a vital ingredient in this cycle. When a supernova doesn't produce dust, it disrupts the recipe. This challenges us to consider alternative paths of matter cycling that might be less efficient or produce different cosmic outcomes. In some ways, dust-free supernovae remind us of how much there is to discover in space. They are tiny clues in a vast cosmic puzzle that stretches across time and space. As we uncover more, we piece together the story of how stars live and die, how galaxies grow, and how everything we know, including ourselves, came to be. So, next time you look up at the night sky, remember that some of the brightest explosions out there might be hiding secrets. Blasts so powerful they clear the dust, leaving behind questions that will keep astronomers searching for answers for generations. Let's keep exploring this fascinating cosmic puzzle. One of the most intriguing questions about dust-free supernovae is how they fit into the bigger picture of the universe's life cycle. We know that dust is essential for many things, like cooling clouds of gas so stars can form, creating the building blocks for planets, and even playing a role in the chemistry that leads to life. So when some supernovae explode and don't leave behind much dust, it shakes up what we thought we knew about the universe's chemical evolution. Dust in space is mostly tiny particles made of elements like carbon, silicon, oxygen, and iron. These dust grains come together in clouds and nebulae, acting almost like cosmic seeds that help gas clump together and collapse into new stars and planets. Without dust, these clouds stay warmer and more diffuse, making star formation much harder. This means dust-free supernovae could affect how quickly or efficiently galaxies grow and change over time. If a large number of stars explode without producing dust, their galaxies might have slower star formation rates or different chemical environments. Over billions of years, this could change the whole shape and history of the cosmos in ways we're only beginning to understand. Scientists are still trying to figure out why some supernovae don't produce dust. One idea focuses on the conditions inside the exploding star. The shock waves, radiation, and temperature all play a role in whether dust can form. In some cases, the explosion may be so violent that dust grains are vaporized almost as soon as they try to form. Imagine trying to build a sandcastle on the beach only to have a huge wave wash it away right after you start. This is kind of what happens with dust in these supernovae. Another factor is the presence of strong stellar winds before the explosion. Some massive stars lose a lot of their outer layers to powerful winds, blowing away material that would otherwise become dust after the star dies. If the star's outer layers are gone before the supernova happens, there's simply less raw material left to form dust. Dust-free supernovae also give us clues about the types of stars that exploded. For example, some supernovae that lack dust seem to come from stars in binary systems, where two stars orbit close to each other. In these systems, the companion star can pull away layers of material, changing how the supernova unfolds. This makes the dust story even more complicated and interesting. Astronomers study these events using many types of telescopes, from X-ray to radio waves, each revealing different parts of the explosion. By comparing these observations, they can estimate how much dust is present, or missing. Sometimes, the data is puzzling. A supernova might show evidence of heavy elements, but no dust, which raises questions about how and when those elements turn into solid grains. One of the ways scientists try to detect dust is by looking for infrared light. Dust absorbs higher energy light and then glows in the infrared. But in dust-free supernovae, this infrared glow is weak or absent. That means the dust either isn't there or it's hidden somehow, perhaps in forms that don't radiate as expected. There's also an interesting debate about whether dust forms immediately after the explosion or if it takes years or even decades to develop. Some supernova remnants that seemed dust-free at first later showed signs of dust forming over time. This delayed dust formation adds a time dimension to the mystery. It could mean that when we observe a young supernova, we might not see the dust that will eventually appear. This raises the question, are dust-free supernovae really dust-free, or just dust late? If dust forms slowly, then maybe many supernovae pass through a dust-free phase before dust starts to appear. This idea could reconcile observations of dust-poor explosions with our understanding of cosmic dust cycles. Another exciting development comes from computer simulations. Scientists use complex models to mimic supernova explosions and dust formation under various conditions. These simulations help test ideas about how dust forms, survives, or gets destroyed in the intense environment of a supernova. By tweaking factors like temperature, density, and chemical composition, researchers can predict when dust will form and when it won't. Simulations suggest that the shape and structure of the exploding star also matter. Some explosions might be asymmetric, with material blasted out unevenly. In these cases, dust could form in certain pockets but not others, making it harder to detect. This uneven dust production could explain why some supernovae appear dust-free while others nearby produce a lot. The study of dust-free supernovae isn't just about the stars themselves. It also impacts how we understand the larger cosmos. Dust grains help form molecules like water and organic compounds in space, which are important for the chemistry of life. If dust production varies, the chances for complex chemistry in different parts of the universe might also vary. This connects to questions about how common life-friendly environments are in the galaxy. Areas with more dust might be more likely to form planets with water and organic molecules, while dust-poor regions might be less hospitable. So, dust-free supernovae could indirectly influence where life might arise. In recent years, astronomers have discovered new types of supernovae that don't fit neatly into existing categories. Some of these show very little dust, sparking fresh debates about how many types of dust-free supernovae might exist. Are we only seeing the tip of the iceberg? Could there be whole classes of explosions we haven't even identified yet? To answer these questions, astronomers are gathering more data from across the universe, including distant galaxies. Studying supernovae billions of light-years away lets us look back in time, to when the universe was much younger. It's possible that dust-free supernovae were more common in the early universe, changing how galaxies and stars evolved back then. This cosmic detective work is ongoing, and every new observation adds pieces to the puzzle. Each dust-free supernova teaches us about the extremes of nature, where matter, energy, and chemistry collide under the most violent conditions. So far, it's clear that dust-free supernovae challenge some of our basic ideas about star death and cosmic recycling. They force us to reconsider how dust forms and survives, how elements spread through space, and how galaxies grow and change. As technology advances and new telescopes come online, we'll get better at spotting these mysterious explosions and understanding their secrets. The next few decades could revolutionize what we know about dust in space, and maybe even how life began on Earth. For now, dust-free supernovae remain one of space's biggest unsolved mysteries. They are like cosmic ghosts, powerful, explosive events that leave behind little trace of one of the universe's most important materials. Their secrets are locked in light, radiation, and particles traveling across space, waiting for us to catch up. That's the amazing thing about astronomy. It's a constant journey of discovery, where the more we learn, the more questions appear. Dust-free supernovae remind us that the universe still holds surprises far beyond what we can imagine, inviting us to look deeper, think harder, and keep searching for answers. The mystery of dust-free supernovae also opens up new ways to think about the life cycles of stars and their remnants. When a star explodes as a supernova, what remains after the blast can be a neutron star, a black hole, or sometimes nothing visible at all. The lack of dust in some supernova remnants raises questions about how these remnants interact with the surrounding space, and how they influence future generations of stars. Neutron stars and black holes are extreme objects formed from the core collapse of massive stars. Neutron stars are incredibly dense. Just a teaspoon of their material would weigh billions of tons on Earth. Black holes, on the other hand, have gravity so strong that nothing, not even light, can escape. Both of these leftovers can affect their environments in different ways, sometimes pushing nearby gas and dust around, sometimes swallowing it. In cases where a supernova leaves little dust, it's possible the blast was energetic enough to clear out or destroy much of the surrounding material. This clearing could slow down or prevent the usual recycling process that turns old stars into new stars, impacting the development of that region in space. Interestingly, dust-free supernovae also have implications for how we measure the universe itself. Supernovae, especially a type called Type I supernovae, are used by astronomers as standard candles to measure cosmic distances. These explosions have relatively consistent brightness, so by comparing their observed brightness to their known intrinsic brightness, scientists can calculate how far away they are. However, if the dust around these explosions is different or missing entirely, it could affect how bright the supernova appears to us. Dust usually dims and reddens the light from distant objects, so a supernova without dust might look brighter or bluer than expected. This can throw off measurements and calculations about the size and expansion rate of the universe. Because of this, understanding dust production, or lack of it, in supernovae isn't just an academic question. It directly impacts how accurately we can measure fundamental cosmic parameters, like the universe's rate of expansion, known as the Hubble constant, and the nature of dark energy, the mysterious force causing the universe's expansion to speed up. Another fascinating angle is the connection between dust-free supernovae and cosmic dust grains found on Earth. Scientists have discovered tiny grains of dust in meteorites. These are called presolar grains because they formed before our solar system existed. Some of these grains are thought to have come from ancient supernovae. By studying their composition, scientists can learn about the conditions in those ancient explosions. But if dust-free supernovae produce little or no dust, then these grains might only come from certain types of supernovae, not all of them. This gives us clues about how different stars contribute to the dust we find in our own solar system. The formation of dust in space is not just about quantity, but also about quality. Different supernovae produce dust grains with different sizes, shapes, and chemical compositions. This diversity affects how dust interacts with light and gas, influencing everything from star formation to the appearance of distant galaxies. For example, carbon-rich dust grains can help form complex organic molecules, while silicate dust can shield regions from harsh ultraviolet radiation. If dust-free supernovae are common, it might mean some regions of space receive less of one type of dust, which can change the chemistry and physics of those environments. One emerging idea is that dust-free supernovae might play a role in the formation of cosmic rays, high-energy particles that travel near the speed of light. The extreme shockwaves from these explosions accelerate particles, which then travel through the galaxy, influencing magnetic fields and even possibly affecting the chemistry of planetary atmospheres. These cosmic rays have been linked to cloud formation on Earth, which can affect climate. So the dust, or lack of it, from supernovae might even have tiny indirect effects on our planet's weather over millions of years. Scientists are also looking into how dust-free supernovae might be connected to gamma-ray bursts, GRBs, the most powerful explosions in the universe. Some GRBs are thought to occur when massive stars collapse to form black holes, and they release intense jets of gamma rays. If these events produce less dust, it might explain why some GRBs appear less obscured by dust clouds than expected. Detecting dust-free supernovae and understanding their properties depends heavily on advances in technology. Space telescopes like the Hubble Space Telescope and the recently launched James Webb Space Telescope, JWST, provide detailed views of supernovae in infrared and other wavelengths, helping astronomers catch signs of dust or its absence. Future missions will push this even further, observing supernovae in more distant galaxies and earlier in cosmic history. This will help build a clearer timeline of when dust production changed over the universe's lifetime, shedding light on how galaxies formed and evolved. What's truly exciting is that dust-free supernovae challenge us to rethink how interconnected everything in the universe is. From tiny dust grains to massive stars and from distant galaxies to our own planet, this cosmic puzzle shows us how every piece matters. We're still far from having all the answers, but the pursuit of understanding dust-free supernovae fuels new discoveries and inspires new questions. Every observation brings us closer to understanding how stars die, how dust lives, and how the universe as a whole keeps changing. So next time you look up at the night sky, remember that hidden among the countless stars are explosions that don't follow the usual rules. They leave no dust behind, yet their impact echoes across space and time, shaping the universe in ways we're just beginning to grasp. The story of dust-free supernovae is a story of mystery, science, and wonder, an ongoing quest to understand the cosmic forces that make everything from stars to planets to life itself possible. Let's delve deeper into the ways astronomers study these unusual explosions and why their discovery has challenged long-standing assumptions about the cosmos. Supernovae have always been seen as powerful factories for dust production. When a massive star explodes, the outer layers, rich in elements like carbon, oxygen, silicon, and iron, are expelled at incredible speeds into space. In the cooling aftermath, atoms combine to form dust grains. These grains then join the interstellar medium, the vast space between stars, where they contribute to the formation of new stars, planets, and even the building blocks of life. But the discovery of dust-free supernovae puts a twist on this classic picture. How do we know some supernovae don't create dust? The evidence comes from careful observations using telescopes sensitive to different wavelengths of light, especially infrared. Infrared light is crucial because dust absorbs visible light and re-emits it in the infrared. So when astronomers observe supernovae remnants, they expect to see a glow in the infrared from warm dust. Yet, for some supernovae, this glow is surprisingly weak or even absent. That suggests either very little dust was made, or that it was destroyed soon after forming. One example is a class of supernovae called type IB/C. These supernovae result from massive stars that have lost most or all of their outer hydrogen and helium layers before exploding. Observations have found that these explosions often show less infrared emission than expected, pointing to minimal dust creation. Why might this happen? One reason could be the extreme conditions inside these explosions. The shockwaves are so violent that newly formed dust grains might be shattered or vaporized before they can survive. Another possibility is that the star's outer layers, which provide the raw material for dust, are already stripped away, limiting dust formation. The dust destruction process is called sputtering. In the hot, fast-moving gas created by the explosion, dust grains collide with energetic particles and atoms that knock atoms off the grains, breaking them down. This can prevent dust from accumulating and surviving. Beyond these physical reasons, the environment around the star before it explodes matters a lot. Some stars live in dense clouds rich in gas and dust, while others are in more empty regions. The amount of pre-existing dust can affect whether the supernova appears dust-free because it influences the amount of material available to be blown outward. Another fascinating aspect of dust-free supernovae is their role in the early universe. Shortly after the Big Bang, the universe was nearly dust-free. The first stars, called population 3 stars, formed from pure hydrogen and helium. When these first stars exploded, they seeded the cosmos with the first heavy elements and dust. However, recent models suggest that some of these earliest supernovae might also have been dust-poor, similar to the dust-free supernovae we see today. This would mean the buildup of dust, and by extension, planets and life, could have been slower and more complicated than previously thought. If the first supernovae didn't produce much dust, then the formation of the first solid objects, including planets, could have taken longer. This insight shapes our understanding of how the universe evolved from a hot, simple gas to a complex web of galaxies filled with stars, planets, and potentially life. It also raises questions about where all the dust in the universe comes from. If some supernovae are dust-free, then other processes must compensate to create the vast amounts of dust astronomers observe in galaxies. One candidate is the giant winds from aging stars called asymptotic giant branch stars, or AGB stars. These stars produce dust slowly over long periods. Another candidate is smaller, less violent explosions called novae, which can also contribute dust to the interstellar medium. By piecing together the contributions from dust-free supernovae and other sources, scientists aim to create a complete picture of the dust life cycle in the universe. Technology continues to push these studies forward. The James Webb Space Telescope, with its powerful infrared capabilities, is already providing new insights. It can peer through cosmic dust clouds to observe the faint infrared glow of dust, or lack thereof, around supernova remnants even in very distant galaxies. Additionally, ground-based observatories equipped with sensitive infrared detectors and radio telescopes tracking molecules in space complement these observations. Together, they build a detailed picture of how dust forms, moves, and is destroyed over time. Dust-free supernovae also help refine models of galaxy formation. Galaxies evolve as gas cools, collapses, and forms stars, with dust playing a critical role by cooling the gas and promoting clumping. If dust production varies significantly, it can influence how quickly galaxies grow and change. Some galaxies, especially young and distant ones seen in the early universe, show surprisingly large amounts of dust. Scientists are still trying to explain how so much dust could form so quickly. Dust-free supernovae add a puzzle piece to this mystery because if many early supernovae produced little dust, other processes must have been very efficient to account for the observed dust. Moreover, dust-free supernovae provide a testing ground for understanding extreme physics. The processes happening inside these explosions involve nuclear reactions, magnetic fields, and relativistic speeds, all under conditions impossible to recreate on Earth. Studying them helps physicists test theories about matter under extreme pressures and temperatures. These studies are not only about space, they also have implications for fundamental physics and materials science. The absence of dust in some supernovae challenges the way scientists simulate these explosions in computers. Many models predicted more dust than observations find, so the discovery of dust-free supernovae forces scientists to rethink key assumptions. This leads to improvements in computational methods, helping scientists create better models of how stars explode, how dust forms, and how galaxies evolve. These models eventually improve our understanding of everything from the life cycle of elements to the formation of solar systems like ours. Looking ahead, the continued study of dust-free supernovae will benefit from upcoming observatories like the Vera C. Rubin Observatory, which will scan the entire sky repeatedly to catch supernovae early and track their evolution over time. With more data, scientists hope to answer questions such as, how common are dust-free supernovae? Are they limited to certain types of stars or environments? Do they follow different explosion mechanisms? And how does their dust, or lack of it, affect the universe on large scales? The answers to these questions will deepen our understanding of the cosmos, and may even shed light on our own origins. After all, the atoms in our bodies were forged in stars, and the dust that helped build the Earth came from ancient stellar explosions. Dust-free supernovae remind us that space is still full of surprises. Even phenomena we thought we understood can hold secrets that challenge our view of the universe. Exploring these mysteries not only satisfies human curiosity, but also enriches our appreciation for the complex, interconnected universe we inhabit. So when you think about the stars, remember that some of their final acts are quieter than we expected, leaving behind little dust but opening vast new questions, guiding us toward the next frontier of discovery. The story of dust-free supernovae invites us to rethink the cosmic balance between destruction and creation. It also pushes us to reconsider how the universe recycles its materials, especially the dust that forms the seeds for new stars and planets. One key thing to understand is how astronomers detect dust, or its absence, when a supernova explodes. When a star goes supernova, it brightens suddenly and dramatically. Over time, as the ejected material expands and cools, conditions become right for dust to condense. But if dust doesn't form or gets destroyed quickly, the expected signals in certain wavelengths won't show up. Scientists use space-based infrared telescopes, like the Spitzer Space Telescope, and ground observatories equipped with infrared detectors to spot these dust signatures. They look for a glow in the mid-infrared range that would indicate warm dust grains. If they don't see it, or if the glow is much weaker than predicted, that suggests the supernova might be dust-free. But that's not the only method. Radio telescopes can detect molecules like carbon monoxide and silicon monoxide that often form in dusty environments. The absence of these molecules also hints at a lack of dust production. Studying dust-free supernovae requires long-term monitoring because dust formation and destruction processes can take years. Sometimes dust is created shortly after the explosion, but then gets blown apart by shocks or heated and evaporated by radiation from the remnant star or surrounding gas. What causes some supernovae to be dust-free while others produce large amounts of dust is a complicated question. It might depend on the type of star, its mass, how it lost its outer layers, or the environment around it. Stars with powerful winds that strip away their outer shells before exploding, for example, might not have enough material left to form dust. Or the intense radiation from the explosion itself could break apart molecules before they can grow into dust grains. Another interesting factor is the explosion's energy. A more energetic explosion creates stronger shock waves and higher temperatures, which may destroy dust grains as fast as they form. On the other hand, less violent explosions might allow dust to survive and accumulate. Then there's the role of magnetic fields. Magnetic forces can influence the movement of charged particles in the expanding gas, which can affect dust grain formation or destruction. This is a cutting-edge area of research, combining astrophysics and plasma physics. The idea of dust-free supernovae also intersects with the study of cosmic dust in other contexts, such as in active galaxies and quasars. These distant, bright objects show large amounts of dust, and understanding dust production mechanisms helps astronomers explain how dust builds up even in the early universe. The more we learn about dust-free supernovae, the more we realize that dust production is a delicate dance, influenced by many factors that can tip the balance toward creating dust or destroying it. Understanding this process is crucial not just for explaining what happens in distant stars but also for understanding the history of our own solar system. The dust that formed Earth and all living things came from ancient stars. If some stars produce little dust, then other sources must have contributed more than we thought. Looking at the bigger picture, dust-free supernovae add a layer of complexity to cosmic chemical evolution, the story of how the universe changed from a simple soup of hydrogen and helium into a rich, diverse environment full of elements, molecules, and solids. Every dust grain tells a story. It is a tiny piece of a star that lived and died millions or billions of years ago. Dust grains collect in clouds where new stars and planets form, carrying the fingerprints of their origins. Scientists analyze these grains, sometimes recovered as meteorites on Earth, to learn about the conditions inside ancient stars. Some grains even preserve isotopes, different forms of elements, that can reveal the processes inside stars before they exploded. Dust-free supernovae, by not producing dust, leave behind different signatures in these grains. Their scarcity or absence helps researchers identify which stars contributed dust and which did not. This, in turn, helps map the history of our galaxy and understand the cycle of matter over cosmic timescales. It connects to big questions about where we come from and how the universe works on both huge and tiny scales. The future holds exciting possibilities. New telescopes, both on Earth and in space, will allow scientists to study supernovae in more detail and in more distant parts of the universe. These observations will help test current theories, discover new kinds of supernovae, and reveal more about the complex relationship between stars, dust, and the interstellar medium. At the same time, laboratory experiments on Earth replicate conditions in supernova remnants to better understand dust grain formation and destruction. By combining observations, simulations, and experiments, scientists are building a clearer picture of these cosmic mysteries. The discovery of dust-free supernovae reminds us that the universe is more varied and surprising than we often imagine. Even the violent deaths of stars can have quiet sides, moments when dust, the building blocks of worlds, simply doesn't form. It's a humbling and thrilling reminder that there's always more to explore, question, and discover. The dust may be missing in these supernovae, but the curiosity and wonder they inspire are very much alive. As we keep exploring the strange world of dust-free supernovae, it becomes clearer that these cosmic events challenge the very assumptions we've held for decades about how the universe recycles matter. You'd think that when a massive star dies in a violent explosion, it would spew out everything: gas, dust, heavy elements. But in some of these supernovae, the dust just isn't there. It's like expecting ashes after a fire and finding none. That's what makes them so fascinating. Now, let's talk about how this absence of dust affects the bigger picture of galaxy formation. Galaxies are filled with stars, but between those stars is a lot of stuff: gas, magnetic fields, radiation, and dust. Dust grains may be tiny, but they play huge roles. They block and absorb light, cool gas clouds so new stars can form, and provide surfaces where molecules can come together. If some supernovae aren't contributing to this dusty cycle, it could mean that we've been overestimating how much material they add to the mix. When galaxies form and evolve, one of the key ingredients is dust. If certain types of supernovae don't produce dust, that changes the timeline. It could mean galaxies took longer to develop the structures we see today, or that other sources of dust, like AGB stars, older red giants, played a bigger role than we thought. Now, here's something even more mind-bending. Some of the most distant galaxies we can see, those from just a few 100 million years after the Big Bang, already have dust in them. But where did that dust come from? The universe was young. There wasn't time for many AGB stars to exist and die. Supernovae were supposed to be the answer. But if many of those early supernovae were dust-free, then we have a new mystery. Who made the dust in the early universe? That question is still up in the air. Maybe we haven't seen enough examples of early supernovae. Maybe some special conditions allowed those first massive stars to make dust more easily. Or maybe something else entirely was responsible, like early black hole activity, or interactions in dense star-forming regions. Dust-free supernovae don't just raise questions, they create whole new lines of inquiry. And one of the tools we're now using to follow those questions is computer simulation. Scientists can't reach out and touch a supernova, but they can build digital versions of them. These models let researchers tweak conditions, like how fast the star spins, how much mass it had, how strong the magnetic field was, and see how it affects dust formation. Through simulations, we've learned that even a small difference in the surrounding environment can change whether dust forms or not. For example, if a star explodes into a low-density region, the gas spreads out quickly and might not be dense enough for dust to clump together. But in a denser environment, the material might slow down and cool enough for dust to start forming. Then there's the matter of what kind of dust is, or isn't, forming. Not all dust is the same. Some supernovae produce carbon-rich dust, others silicates, and others even more exotic materials. In dust-free supernovae, we don't just see a lack of dust, we see a lack of specific types of dust that we'd expect based on the star's composition. For instance, some stripped envelope supernovae, stars that lost their outer layers before exploding, are often dust-free. They don't produce much, if any, carbon dust, even when their interiors should have been rich in carbon. That suggests something's happening in those explosions that destroys carbon-based grains or prevents them from forming in the first place. Radiation could be the culprit. When a supernova explodes, the light it gives off is incredibly intense. This radiation can photoevaporate dust grains, basically, break them apart before they can fully form. If the radiation lasts long enough or is powerful enough, even sturdy dust grains like silicates can get wiped out. Another possibility is the reverse shock. After the initial explosion, a wave of material rushes outward into space. But that's not the end of it. That expanding material slams into surrounding gas and sends a shockwave back inward, a reverse shock. This shock moves through the inner layers of the explosion, heating and compressing everything in its path. Dust grains that survive the initial explosion may get shredded, vaporized, or smashed into smaller bits that don't survive as independent grains. So, dust-free supernovae might not be entirely dust-free. Some dust might form, only to be destroyed within months or years. That would make them dust-failed, or dust-erased supernovae. It's a subtle difference, but it changes how we interpret their signals and how we factor them into galactic evolution models. Let's bring this back to something more relatable. Imagine you're trying to track how much sugar a bakery uses over a year. If you think every cake uses the same amount of sugar, your estimate might be way off if some of those cakes are actually sugar-free. That's what happens with dust-free supernovae. If we assume every exploding star is creating dust and they're not, we'll misjudge how much dust exists in the universe, and that affects every part of the cosmic recipe. And don't forget, we're just now entering an era where we can detect fainter, farther supernovae thanks to telescopes like the James Webb Space Telescope. JWST is especially good at seeing in the infrared, the perfect wavelength range for detecting warm dust. It's already helping scientists spot dusty and dust-free supernovae at greater distances, meaning we're finally starting to build a real statistical sample instead of guessing based on just a few examples. In fact, the early results from JWST are showing us that the dust production of supernovae is even more varied than we thought. Some supernovae are dust factories, producing massive amounts of solid particles. Others seem to be total duds when it comes to dust. That variety means there's no single answer. Each supernova is its own story, shaped by what came before and what's around it. This also connects to something really strange, the cosmic dust budget. Basically, when scientists try to add up all the dust in galaxies and compare it to how much dust we think supernovae and stars can make, the math doesn't always add up. Sometimes there's too much dust. Sometimes not enough. Dust-free supernovae are part of that puzzle, because if more of them are dust-free than we assumed, then we're underestimating the role of other dust sources, or we're missing something fundamental about how dust forms and survives in space. And there's a philosophical angle here too. Dust may seem boring, it's just little specks floating around, but it's literally the stuff we're made of. Every solid part of you, your bones, your teeth, your cells, came from dust grains that formed in long-dead stars. If certain stars don't make dust, then your atoms didn't come from those explosions. You are, in a real sense, the child of the dusty ones, not the dust-free. This gives dust-free supernovae a poetic twist. They are the ghosts of stars that left no seeds. They shone bright, but didn't leave behind the grains that make new worlds. Their beauty lies not just in what they do, but in what they don't do. They're the silent gaps in the cosmic cycle, the missing pieces in the great puzzle of how everything came to be. And we're only just beginning to understand them. But if dust-free supernovae are out there hiding in plain sight, how many of them have we already seen without realizing what they were? That's a question researchers are now asking more seriously. For years, when astronomers observed a supernova and didn't see evidence of dust, they often just assumed it was too early, or the dust was too faint to detect. But what if that wasn't the case? What if we were seeing actual examples of stars that simply didn't leave behind any dust? This realization is changing how scientists re-examine old data. Astronomers are going back to archived observations of past supernovae, comparing light curves, analyzing spectra, and searching for any faint infrared signals they might have missed. Some of the so-called normal supernovae might actually be the dust-free kind. And that's critical, because if a larger portion of supernovae are dust-free than we thought, it affects not just individual star evolution, but also the entire understanding of how galaxies build up their material over time. Now think about this. If you're trying to simulate the formation of galaxies over billions of years, you need to know how much dust each generation of stars leaves behind. Dust cools gas clouds, helps form new stars, and even shapes how light moves through a galaxy. Dust-free events throw a wrench into those simulations. They mean some regions might take longer to become fertile grounds for new stars. It changes the timing, the chemistry, the structure. It's like taking flour out of a bakery. You can't make bread as easily without it. Dust-free supernovae also change what we understand about early cosmic history. Like we touched on earlier, many of the most distant galaxies already have tons of dust, but if early supernovae weren't efficient at making that dust, then someone, or something, else was doing it. This leads to speculation. Maybe early stars were different. Maybe they exploded differently. Maybe the early universe was somehow better at making dust. Or maybe there's a process we still haven't discovered yet. Some researchers have suggested that there might have been exotic stars in the early universe, population 3 stars, that formed from pure hydrogen and helium, the very first elements. These stars were huge, short-lived, and extremely powerful. If they went supernova, they could have produced the first real dust grains in the universe. But here's the catch: we've never actually seen a population 3 star. Not even one. Their existence is theoretical. So we're stuck in this bizarre place where we need their dust to explain what we see, but we can't prove they were ever there, yet. And let's go even deeper. There's a link between dust, light, and the cosmic background itself. Cosmic dust affects how we see the universe. It blocks light from distant stars and galaxies, which means that without dust, we would see more light. But that also means that places or events with less dust might appear brighter than they should, or mislead us about what's actually happening. Dust-free supernovae might therefore skew how we interpret light from the early universe. That could even influence how we understand things like cosmic acceleration or dark energy, because dust affects the brightness of standard candles like Type I supernovae, which are used to measure the expansion of the universe. So if some of those standard candles are dust-free and others are not, and we don't account for that difference, it can throw off the whole calculation. It's like using 2 types of light bulbs to measure distance, but forgetting that one of them burns brighter than the other. That's how subtle, and how important, these differences really are. And let's not forget the chemistry. Dust is more than just debris. It's made of specific elements: carbon, oxygen, silicon, magnesium, and more. If a star explodes and doesn't make dust, where do those elements go? Are they scattered as individual atoms? Do they combine into gases that drift away forever? Or are they recycled in another way entirely? That mystery touches on the life cycle of elements, what astronomers call nucleosynthesis. It's the idea that every atom of calcium in your bones, every molecule of oxygen in your breath, was forged inside a star. Supernovae are supposed to be the final act in that cycle, spreading those elements across space. But if they explode without creating the dust that helps carry and shield those elements, the story changes. Maybe more material ends up ionized and escapes detection. Maybe it takes longer to get recycled into new stars and planets. And speaking of planets, there's another fascinating angle here: planet formation. Dust grains are the building blocks of planets. In young star systems, tiny dust particles collide and stick together, growing into pebbles, rocks, and eventually whole worlds. If supernovae don't produce dust, that means fewer raw materials to make planets. That might not seem like a big deal when you're thinking about a single supernova, but scale that across a galaxy, and over billions of years, and suddenly it starts to matter. Some regions of the galaxy may end up richer in planet-making material than others, simply based on whether their stars were dusty or not. Even life itself could be affected. The presence or absence of dust influences where planets form, how atmospheres develop, and even what kind of organic molecules are available. Dust carries complex chemistry. Without it, the early universe might have had a much harder time jump-starting biology. That puts dust-free supernovae right at the edge of the biggest question of all: why are we here? It's not just a cosmic curiosity. It's a fundamental piece of the origin story. And yet, these supernovae are still poorly understood. We don't know exactly how common they are. We don't know exactly which conditions lead to their dustlessness. We don't know how long their effects last, or whether they're more common in certain types of galaxies. All of this opens up room for discovery. In the next few decades, as we gather more data from instruments like JWST, the Vera Rubin Observatory, and even the next generation of space-based infrared telescopes, we'll be able to build better models. We'll observe more explosions and more wavelengths and get a clearer picture of when and how dust forms, or fails to. We'll also be able to answer questions we haven't even thought to ask yet. Like, could some galaxies evolve without any help from supernova dust at all? Could they rely entirely on dust from AGB stars or other sources? Could some regions of the universe be dominated by dust-free supernovae? And what would those galaxies look like? Would they be more transparent? Would their star formation rates be lower? Every one of those questions adds another layer to the mystery. And the coolest part? We're living at a time where we get to ask those questions. A few decades ago, we didn't even know this was a thing. Now, dust-free supernovae are one of the most exciting puzzles in astrophysics. They're forcing us to rethink what we thought we knew about how stars die, how galaxies grow, and how matter itself is recycled through the cosmos. And if there's one thing the universe keeps teaching us, it's this: the more we learn, the stranger it gets. But let's not stop there, because this rabbit hole goes even deeper. Imagine watching a star explode in real time. With the telescopes we have today, we can catch the light from a supernova within hours of it happening. That light carries with it secrets about the star's last moments. And with dust-free supernovae, it's like watching an explosion in a room without smoke. You can see right into the core of the chaos. That clarity is rare in space. Most cosmic events are fogged up by dust, scattered by particles, and obscured by time. But these supernovae? They give us a front-row seat to the death of a star with nothing in the way. This is where spectroscopy becomes key. By analyzing the light from a dust-free supernova, scientists can break it down into its component colors and identify exactly which elements are present, how fast they're moving, and what temperatures they're at. And because there's no dust muddying the signal, the data is cleaner than usual. That's how we're starting to notice that some of these supernovae are different, not because of what we see, but because of what we don't see. No absorption by dust. No re-emission in the infrared. Just raw starlight and expanding gases. Some researchers have taken this a step further by using computer simulations to model what happens when a supernova explodes in a low-dust environment. And what they've found is surprising. Without dust, the shockwave moves differently. The gas expands more freely. Radiation escapes faster. And this can even alter the shape of the supernova remnant, the glowing cloud that lingers for centuries after the explosion. In dusty environments, remnants tend to be more clumpy and irregular because the dust gets mixed in with the gas. In dust-free conditions, they're smoother, more symmetrical, and sometimes fainter because there's no dust to scatter or trap light. These differences matter. They help scientists distinguish between different kinds of supernovae. For example, if you see a symmetrical, clean-looking remnant with a fast-fading light curve, it might be a dust-free supernova. And that could tell you something important about the star's environment. Maybe it lived in a galaxy that didn't have a lot of heavy elements. Maybe it exploded before it had time to form a thick envelope of material. Or maybe it was just a strange kind of star altogether. And that brings us to another big question. Are dust-free supernovae linked to specific types of stars? Some astronomers think the answer is yes. There's growing evidence that dust-free supernovae are more common in low metallicity environments, places where stars have very few heavy elements. These environments tend to exist in the early universe or in small, primitive galaxies that haven't had many generations of star formation. In these conditions, stars can't form as much dust during their lifetimes because they simply don't have the raw materials to do so. So when these stars explode, there's not much dust to begin with. That fits with what we're seeing in some of the most distant galaxies. But it also challenges our assumptions about how stars evolve in these environments. For decades, astrophysicists assumed that all supernovae would produce at least some dust. Now we're learning that might only be true in certain chemical settings. The rules are different when the ingredients are different. But even in our own galaxy, there are hints of dust-free supernovae. Observations from telescopes like Spitzer and Hubble have revealed remnants that are mysteriously clean. No dust emission, no thermal signatures, just gas and radiation. In some cases, astronomers were baffled by the lack of dust, assuming maybe it had dispersed too quickly or hadn't formed yet. But as more examples pile up, it's getting harder to write them off as anomalies. They might actually be a distinct category of stellar death. And then there's the wild card in all of this, dark matter. No one really knows if there's any link between dust-free supernovae and dark matter. But some researchers have speculated that in regions with high concentrations of dark matter, the dynamics of a supernova could be subtly altered. Maybe dark matter affects the distribution of mass. Maybe it interferes with how shockwaves travel. Maybe it even influences dust formation on a quantum level. That's all highly speculative, of course, but it shows how wide the implications of this mystery really are. The truth is, dust-free supernovae raise questions that go beyond just stars. They touch on galaxy evolution, planetary systems, chemical enrichment, and even the origins of life. They're a missing link in the cosmic chain, a phenomenon that we're only beginning to understand. And it's not just a matter of better technology. It's also a matter of better theory. Scientists are now rewriting their models of stellar evolution to include scenarios where dust doesn't form. That changes how we simulate everything from star clusters to galaxy collisions. It affects our predictions about where planets might form, how fast galaxies age, and how visible certain regions of space should be in different wavelengths. In fact, some of the dark galaxies we've detected, ones that barely emit any visible light, might not be dark because they're empty. They might just be full of dust-free supernovae that don't leave behind the usual glowing mess. That's a wild idea, but one that's starting to gain traction as more data rolls in. Even the cosmic background radiation, the faint glow left over from the Big Bang, might be affected by this. If more supernovae were dust-free than we thought, then the buildup of cosmic dust over time was slower than expected. That would influence how the background radiation was absorbed and re-emitted over billions of years. It might even mean our models of early cosmic temperatures need adjusting. And then there's the human angle. Every breakthrough in space science has a ripple effect on technology. The detectors we use to study supernovae end up being used in medical imaging. The algorithms we develop to filter out noise in a signal get used in telecommunications. The materials we invent to build better telescopes turn into components for everything from cars to smartphones. So studying dust-free supernovae isn't just about understanding the universe. It's about pushing the boundaries of what we can see, measure, and build. And that's the beauty of it. A mystery that starts with a missing puff of dust from a dying star ends up influencing everything from the formation of planets to the chips in your computer. That's the kind of cosmic connection that makes astronomy more than just stargazing. It's a lens into how everything fits together. And the best part? We've only just scratched the surface. Now, let's pull back and think about something that changes the game entirely. What if dust-free supernovae are not just a rare exception, but a common phenomenon we've just been missing this whole time? That idea might sound wild at first, but think about how we detect supernovae. Most of our surveys are tuned to pick up the bright, colorful, and dusty ones, because those leave big signatures in infrared and visible light. The dusty clouds make them more obvious. But if a supernova explodes without creating dust, its light behaves differently. It might peak faster, fade quicker, and not show up as clearly in certain wavelengths. In fact, it could be hiding in plain sight, just not lighting up the parts of the spectrum we usually look at. This is where some recent discoveries are starting to make astronomers rethink the numbers. A few large-scale surveys, like those done with the Zwicky Transit Facility and the Vera Rubin Observatory, coming online soon, are uncovering fast transients, bursts of light that come and go much faster than traditional supernovae. Some of these don't fit the usual mold. They're brighter than novae but dimmer and quicker than most supernovae. And they show little to no signs of dust in the aftermath. Are these just flukes? Or are they dust-free supernovae happening all around us, just too fast or faint for our old instruments to catch? If it turns out these events are more common than we thought, that could completely change our picture of how many stars die, and how they die. It might also explain why certain galaxies seem to have fewer dust lanes or less interstellar material than expected. Maybe they're not lacking supernovae, They're just home to dust-free ones that don't leave behind the usual debris. And here's another twist. What happens to the leftover material when there's no dust? Usually, dust helps cool down the remnants of a supernova. It slows things down, gives atoms something to latch onto, and helps new molecules form. But without dust, everything stays hotter longer. That might affect how fast neutron stars cool off. It might impact whether a black hole forms at all. It might even influence how much radiation escapes into space. Think of it like a fire burning in open air versus one burning in a foggy, smoky room. The first one radiates more heat and light out into the surroundings. The second one is muffled. Same energy, different outcomes. Dust-free supernovae are like that open-air fire, burning hot and clean, sending shockwaves of energy out into space with fewer barriers. That raw energy could impact neighboring stars, strip atmospheres from nearby planets, or even trigger the birth of new stars in surprising ways. That's right, supernovae don't just end things. Sometimes they begin them. When a supernova explodes, it sends a shockwave into surrounding space. That shockwave compresses gas clouds, and in the right conditions, that compression is exactly what's needed to kickstart the birth of new stars. In dusty environments, that process is slow and uneven. The dust gets in the way, absorbs some of the energy, and spreads it out. But in dust-free areas, the shockwave moves faster. It hits harder. It's like a pressure blast with no cushion. That could spark rapid star formation in nearby clouds, faster than we'd expect in dusty regions. So now you have a whole new cycle. A dust-free supernova blows up, its energy hits a nearby gas cloud, and that cloud collapses into a cluster of new stars, possibly forming in a cleaner environment that might also lead to more dust-free supernovae. It's a feedback loop. A chain reaction. One that could reshape parts of a galaxy over time without leaving the usual dusty fingerprints. And now we've come to one of the biggest open questions in all of this. How do dust-free supernovae affect our search for life? It might sound unrelated at first, but think about it. Dust plays a huge role in shaping planets. Dust grains are the building blocks of everything solid: rocks, moons, planets, even you and me. If an area of space has fewer dust-producing supernovae, that could change what kinds of planets form. Maybe it limits the formation of rocky worlds. Maybe it tips the balance toward gas giants. Or maybe it just delays the whole process, slowing down the growth of planets and giving life less time to get started. But here's the twist. Fewer dusty supernovae might also mean fewer high-energy particles bombarding young planets. Dust tends to trap radiation. Without it, that radiation escapes more freely, but also more cleanly, with fewer lingering effects. That might create periods of lower background radiation in some regions, which could actually help life develop in the long term. It's a weird trade-off. Less dust might mean fewer raw materials, but also fewer disruptions. We don't know yet what the balance looks like. We're still gathering the data. But the implications are huge. If dust-free supernovae are more common in certain galaxies or regions, that could influence whether those areas are more or less likely to support life. It could even affect the design of future space missions. If we send probes to a galaxy with a history of dust-free supernovae, we might need to rethink how we study its planetary systems. We might not find the same types of atmospheres or mineral compositions we're used to. And we haven't even touched on the way these supernovae affect cosmic timelines. One of the ways scientists try to map the history of the universe is by counting the number of supernovae over time. That count gives us a rough idea of how many stars have lived and died. But if dust-free supernovae are being missed, or mistaken for something else, then our timelines might be skewed. We might be underestimating how fast stars were dying in certain eras. We might be missing entire epochs of stellar evolution. That could throw off everything from our models of galaxy growth to our estimates of cosmic age. And it gets even weirder when we bring in gravitational waves. You've probably heard about how massive events like neutron star collisions and black hole mergers send ripples through space-time. Some supernovae can do that too, especially if they collapse into black holes or explode asymmetrically. But if dust-free supernovae are more compact, more symmetrical, or faster fading, they might produce different gravitational wave signatures than the ones we're used to. That means some of the weird wave detections we've seen, ones that don't quite match known patterns, might actually be dust-free supernovae in disguise. Imagine that, invisible explosions sending out waves through space-time, leaving no dust, no light, just a subtle tremor in the fabric of the universe. That's the kind of mystery we're dealing with here. Not just an astronomical oddity. Not just a cleaner version of something we already knew. But a whole new window into how the universe works, how stars live, how they die, how they pass on their legacy to the galaxies around them, and how their silence can sometimes be louder than their explosion. And the more we study dust-free supernovae, the more we realize that the universe isn't just a place of bright lights and big bangs. Sometimes, it's the missing pieces, the quiet spaces, the unexpected gaps, the lack of dust, that tell the most powerful stories. And here's where the mystery of dust-free supernovae gets even deeper. What if their existence hints at something more fundamental about the way matter behaves at the end of a star's life? Normally, when a massive star explodes, it throws off its outer layers, hydrogen, helium, heavier elements, and the dust forms out of the cooling gas. But in a dust-free supernova, this isn't happening. So now we have to ask, why not? Is the explosion itself too hot for dust to condense? That's possible. If the shockwave is intense enough and the energy too concentrated, it might keep the surrounding material too hot for long enough that dust grains never get a chance to clump together. But even that only scratches the surface. Because this leads to a more uncomfortable possibility. Maybe, in some of these cases, there is no outer layer to throw off. That would mean some dust-free supernovae are coming from stars that have already shed their outer layers before they explode. Imagine a stripped-down core, already exposed to space, just waiting to collapse. When it does, there's very little gas left to form dust. And if that's the case, then these stars were already different long before they died. They might have been in binary systems, where a companion star siphoned off their outer layers. Or maybe they were losing mass through powerful winds over millions of years. That would mean dust-free supernovae aren't just a different outcome, they're a sign of a whole different life. These stars lived faster, burned hotter, lost more, and exploded cleaner. They may even be ancestors of some of the most exotic objects in the universe, like magnetars, quark stars, or even black holes that form without the typical supernova flash. And now, here's the real kicker. These cleaner deaths may be a clue that we've misunderstood what counts as a supernova altogether. In astronomy, categories often come from how something looks, not necessarily how it works. We classify supernovae by their light curves, by the presence or absence of hydrogen, by how long they shine. But if a supernova skips the dust stage, it might also skip the bright, lingering glow. It might explode fast, cool fast, and fade fast. Some might not even register as supernovae at all. They might just be flashes, anomalies, odd data points we don't know what to do with. In fact, there's already a name for some of these mysteries. Fast blue optical transients, FBOTs. These are strange flashes of light that appear in distant galaxies and vanish quickly. They're hotter and shorter-lived than typical supernovae, and some of them, like the now famous COW event, defy almost every model we have. They don't create dust. They're too fast. Too bright. Too blue. Sound familiar? Some scientists think FBOTs and dust-free supernovae could be the same thing, or at least cousins. And if that's true, then this is a much bigger phenomenon than anyone thought. It's not just a weird side story. It could be a major missing chapter in the life cycles of stars. And now let's talk about the strange effect these explosions have on their surroundings. You see, a dusty supernova enriches space with carbon, silicon, iron, elements that seed planets and solar systems. A dust-free supernova might still release those elements, but they spread differently. Without dust grains to cling to, atoms drift farther, more freely, and potentially in different patterns. The whole way elements move through galaxies could be different in dust-free zones. That could mean that the elemental makeup of a region of space might tell us about its supernova history. It's like forensics, but cosmic. You look at the ratios of certain elements, the distribution of metals, and you can start piecing together what kind of explosions happen there, and how often. And when astronomers do this, sometimes they find regions that don't make sense, areas that have too few heavy elements, or patterns that don't match the known dust-producing supernova types. And suddenly, the dust-free theory starts to look like an answer. This isn't just a curiosity. It could reshape everything from galactic chemistry to planetary science. Because if the metals and dust from explosions don't go where we think they go, then how can we accurately model the evolution of planets, moons, or even the conditions needed for life? And while we're here, let's stretch this even farther. Could dust-free supernovae help explain the Fermi paradox? The Fermi paradox, as you probably know, is the mystery of why we haven't seen signs of alien civilizations. One possible reason? Maybe the parts of the universe where life could evolve are much rarer than we think. Maybe in regions dominated by dust-free supernovae, there's simply less dust, fewer rocky planets, fewer stable environments. So life doesn't get started, or gets wiped out more easily. These cleaner explosions might be purifying the galaxy, in a sense, but also making it harder for life to gain a foothold. It's a haunting idea that some of the most violent, beautiful events in the universe might also be preventing life from flourishing in the way we expect. Or they could be helping it. Because there's another angle to this. In areas with lots of dust, light doesn't travel as far. Stars are obscured. Radiation lingers. But in dust-free regions, light cuts clean across the galaxy. Energy spreads more evenly. Radiation isn't trapped. That could mean more stable long-term conditions for any planets that do form. The kinds of conditions that might, over billions of years, give rise to something that asks the big questions. Something like us. And think about this, if we're just now discovering dust-free supernovae, what else might we be missing? The universe is vast. We've only seen a tiny fraction of it, and most of what we do see is shaped by the tools we use. If our telescopes are tuned to find certain kinds of explosions, then those are the ones we'll keep finding. But what if we're blind to a whole category of stellar deaths? That's the kind of realization that keeps astronomers awake at night. Not because it's scary, but because it means there's so much more to learn. It means the story of stars, the story of the universe, isn't finished. It's still unfolding. And dust-free supernovae might be one of the biggest missing pieces. And if dust-free supernovae are a missing piece of the puzzle, then we have to go all the way back to the beginning, to how stars form, how they live, and what truly causes them to die the way they do. Because if a star dies without dust, that means its entire life was likely different. The kind of matter it pulled in. The kind of reactions that powered it. The kind of environment it existed in. Everything may have been set up from the very beginning to create this clean, sudden end. Most of us imagine stars being born from dense clouds of gas and dust. These clouds collapse under gravity, heat up, and start nuclear fusion. That's the classic image. But what if some stars form in areas where there's very little dust to begin with? What if they're born in cleaner regions of space, maybe after previous dust-clearing events or after supernovae that didn't create any dust either? This would create a kind of feedback loop, clean stars creating clean deaths, which then lead to more clean star formation. Now we're talking about a galactic ecosystem, a cycle of clarity. That would be a game changer, because most of our understanding of galaxy evolution involves a kind of balance between dusty regions and clear ones. If there are whole swaths of galaxies where stars are forming, living, and dying without dust, then all our models of star population, light absorption, and even gravitational dynamics might need rethinking. And this gets even more interesting when you realize how much dust affects what we see. Dust doesn't just make things, it hides things. It absorbs and scatters light, which means that in dusty galaxies, we're often seeing just the tip of the iceberg. We miss dim stars, we underestimate the energy output, and we misread the color and brightness of objects. But in areas with dust-free supernovae, that hiding effect is gone. The light is raw, unfiltered, and clear. This means we might be able to use these supernovae as cosmic lighthouses. Bright, unclouded flashes that reveal the true structure of the universe. When a dusty supernova goes off, its light can be heavily absorbed by surrounding material, which distorts our measurements. But a dust-free one? It punches right through. It gives us pure data. And if we can find enough of them, we might use them to map the cosmos more accurately than ever before. Imagine aiming our telescopes at a galaxy cluster billions of light years away and spotting a dust-free supernova exploding in the middle of it. That explosion wouldn't just be an event, it would be a tool. It would light up the region, acting as a temporary flashlight to reveal things we might otherwise never see. It could expose distant stars, unseen matter, and gravitational lensing effects. It might even help us test dark energy. Yes, dust-free explosions might help us understand the very thing that's making the universe expand faster. You see, we use certain kinds of supernovae, like type I, as standard candles. These are explosions with predictable brightness, which we use to measure cosmic distances. But dust throws off those measurements. If we overestimate how much light is absorbed by dust, we could miscalculate how far away something is. That's a big deal when you're using that data to figure out the size, shape, and speed of the universe itself. Dust-free supernovae, by contrast, offer a kind of unfiltered truth. No guessing about how much light was lost. No compensation for scattered wavelengths. Just a clean, bright signal that we can trust. And in astronomy, trust is everything. This is why some researchers are starting to think dust-free supernovae might be the key to solving some of the biggest cosmic mysteries. They don't just tell us about how stars die, they help us understand the fabric of reality. But here's the thing, we still don't fully understand how often these supernovae happen. Because they're harder to spot. Dust itself can make explosions more visible in the infrared spectrum, thanks to the glow of heated grains. Dust-free supernovae, on the other hand, cool rapidly and don't linger. That means they might be all around us, but we're simply missing them. Think about it. How many bright flashes in old survey data went unclassified because they disappeared too fast? How many were dismissed as false positives or artifacts, just because they didn't behave like the supernovae we're used to? And what if there's a whole spectrum of dust-free supernovae, different types, caused by different mechanisms, from different kinds of stars? What if we've only seen the beginning? Let's go back to that idea of stripped envelope stars, those that lose their outer layers before they explode. These could be Wolf-Rayet stars, which are already some of the hottest, most extreme stars in the universe. They blast away their own hydrogen layers with intense stellar winds. When they finally die, they might not have anything left to make dust with. Or consider white dwarfs in binary systems. These are the kind that explode as type I supernovae. If the surrounding area has already been swept clean by previous activity, say, by the companion star's radiation, then the explosion might be essentially dustless. And then you've got the possibility of direct collapse black holes. These are stars that don't even go supernova in the traditional sense. They collapse inward so fast, and so violently, that barely any matter escapes. No dust. No remnants. Just a sudden vanishing act. And what little light does escape might resemble a dust-free supernova if we happen to catch it at just the right moment. So in that sense, dust-free supernovae might not be one single phenomenon. They could be a collection of edge cases, outliers in every direction, that just happen to share one thing in common, a clean, fast, dustless death. But here's a curveball, what if the dust is there, and we just can't see it? That's another possibility researchers are considering. Maybe the dust that forms in these explosions is different. Maybe it's made of elements or particles that don't reflect or absorb light in the usual way. Exotic compounds, ultra-fine grains, or even weird molecular structures that don't show up in our infrared observations. It's possible that our instruments just aren't sensitive to the kind of dust being formed. And if that's true, then dust-free supernovae aren't really dust-free. They're just invisible in a certain way. That would mean we've been misled not by the stars, but by our own tools. It's a classic problem in science. We interpret the universe through the lens of our instruments, our models, and our assumptions. And sometimes, that lens isn't clear. Sometimes, We miss things because we're not looking in the right way. That's why new telescopes like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, are so important. They'll help us peer deeper into the infrared spectrum, catch faster events, and analyze explosions in more detail than ever before. We might finally be able to tell if these dust-free explosions are truly clean, or just hiding something new. Or maybe, just maybe, we've been underestimating the timeline of how fast dust can form. You see, in traditional supernova models, dust takes time to condense. The initial blast is so hot, so chaotic, that atoms and molecules don't have time to come together into stable grains right away. But what if in some supernovae, the conditions shift so quickly, or so violently, that dust doesn't get a chance at all? Not later, not ever. That might seem simple, but it would completely rewire how we understand the life cycle of elements in space. Because dust isn't just clutter, it's how complex chemistry starts. It's the stuff that clumps into planets. It's what allows molecules to stick together and form the seeds of life. If some regions of the universe are missing that step, it means they might also be missing out on the building blocks of everything else. And think about what that implies. If dust-free supernovae are common in certain galaxies, those galaxies might struggle to form planetary systems. Or the planets they do form might be different, rockier, less carbon-rich, maybe lacking the kinds of compounds that make atmospheres breathable or oceans stable. In short, entire galaxies could be hostile to life simply because their stars don't leave behind the right kind of debris. That's a wild idea. A single factor, dust production in stellar explosions, might decide whether a galaxy is habitable or barren. This leads us to one of the most mind-blowing possibilities. If you trace the chemistry of life on Earth, carbon, oxygen, nitrogen, iron, you'll find that most of it comes from stars that lived and died billions of years ago. Much of that material was seeded by supernovae, and a lot of it was carried by dust. So if the earliest supernovae in the universe were mostly dust-free, then the first galaxies might have been chemically sterile for a long, long time. And if that's the case, maybe life didn't just need stars to form. Maybe it needed the right kind of stars to die. That kind of idea rewrites the entire narrative of cosmic history. Instead of thinking of the universe as one big chemical machine that slowly got richer over time, we have to start thinking about it as patchy, uneven, with pockets of development and stagnation. Places where dust was made, and places where it wasn't. Places where life could begin, and places where it never even had a shot. But let's get back to the science for a second. How exactly do astronomers know when a supernova has no dust? It comes down to something called the spectral energy distribution. When light from a supernova reaches our telescopes, it comes in different wavelengths, from high-energy ultraviolet to visible light and long-wavelength infrared. Dust usually emits most strongly in the infrared, because it's warm but not hot. If we look at a supernova and don't see that characteristic bump in the infrared spectrum, it tells us something is missing. And when that pattern repeats across multiple observations, different telescopes, different teams, different years, it's hard to ignore. Some studies have pointed to specific supernovae where this happened. For instance, SN 2006 JC showed almost no dust features despite being well studied. Its explosion was bright, fast, and surprisingly clean. Others, like SN 2010 JL, initially seemed dust-rich, but later analysis suggested something more complicated. Perhaps the dust formed after the initial explosion, in a slower outer shock. But that raises another question: what if we're looking at the timing all wrong? Maybe some dust-free supernovae do make dust, but not right away. Maybe it forms slowly, years after the explosion, as the remnants cool and interact with the interstellar medium. That would make them hard to classify, because their infrared signatures would appear much later than we're used to checking. This is why long-term monitoring matters. If we just take a few snapshots and walk away, we might miss the full story. Dust is slow. Stars are fast. And if we're too focused on immediate data, we won't see how things evolve. That's why missions like JWST, the Vera C. Rubin Observatory, and even amateur astronomer networks are so important. They're watching the skies for longer, looking deeper, and catching the kinds of anomalies we used to overlook. They're building the timelines we need to really understand how these explosions behave, what happens in the first few seconds, and what lingers for years. And the more we look, the more strange cases we find. Like stars that seem to explode twice, first a flash, then a bigger burst weeks later. Or explosions that leave behind no visible remnants at all. Or ones that cool so fast they almost vanish from our instruments before we even realize what happened. These could all be different flavors of dust-free supernovae. Or they could be entirely new categories we haven't even named yet. The truth is, we're still flying blind in a lot of ways. Even the best telescopes only see a tiny fraction of the universe. Light takes time to reach us, and by the time it does, entire galaxies may have changed. Stars may have lived, died, and disappeared without us ever knowing. That's why every dust-free event we do catch is valuable. It's a clue. A crack in the curtain. A flash of something we weren't expecting. And this brings us to an idea that's both fascinating and a little scary. What if dust-free supernovae are actually the default? What if the dusty ones are the outliers, not the norm? That flips everything. It suggests that most stars might die cleanly, and that it's only under rare conditions that dust is made. If true, that would completely reframe how we think about cosmic dust budgets, element formation, and the evolution of galaxies. It would mean the universe is less dusty than we thought. And that would make it brighter, hotter, more visible, maybe even more dangerous. Because dust plays another role: it protects. It cools down regions of space. It shields delicate molecules. It filters radiation. If the universe had less of it, then maybe early galaxies were more hostile, more exposed. Maybe cosmic rays tore through young systems, sterilizing them before life could begin. Maybe the first Earth-like planets never had a chance. Or maybe they did. And we're the result of a narrow window, a moment when stars died just right, in just the right place, producing just enough dust to make planets, air, water, and life. It's a staggering thought. And it all begins with a few explosions that didn't behave the way we expected. Now, let's peel back another layer of this strange mystery. We've been asking why some supernovae produce no dust. But what if the answer isn't just about the star, or its explosion? What if it's about the environment it exploded into? Imagine a supernova going off in a part of space that's already empty, devoid of material. Maybe it's inside a void, or on the outer edge of a galaxy where the interstellar medium is thin. In that kind of place, even if the explosion produces dust, there's nothing for that dust to interact with. No gas clouds to slow it down, no radiation to heat it, no matter to clump around it. The dust just floats off, cold and invisible. We might not even notice it. Or worse, maybe the dust gets destroyed before it can even settle. Because here's the harsh reality of space: just making dust isn't enough. You also have to protect it. And in the chaos of a supernova, protection is hard to come by. The shockwave alone can move at tens of thousands of kilometers per second, ripping through space and smashing anything in its path. If the dust forms too close to the blast, it could be vaporized almost instantly. If it forms too far out, it might never show up in our instruments. There's a narrow sweet spot where dust survives. And that spot might only exist in certain kinds of explosions. We know that Type 2P supernovae, the kind with a plateau in their brightness curve, are more likely to produce dust. They explode slower, more gradually, which gives molecules time to form. But Type IB and IC supernovae, which shed their outer layers before the blast, tend to be cleaner. And Type I supernovae, the kind used to measure the expansion of the universe, show very little dust at all. So maybe dust-free supernovae aren't weird, they're just a natural result of the star's structure. That leads to another important point: the chemistry of the star itself might matter more than we thought. A star rich in carbon might make more dust than one dominated by oxygen. A star with lots of silicon might produce different types of grains, maybe quartz-like structures instead of carbon soot. And if the ratios are off, or if the star's mass is too low, the conditions for dust formation might never occur. It's like baking. You need the right ingredients, in the right amounts, under the right heat. And if anything's off, too much heat, not enough time, missing an element, the whole thing collapses. You get a failed cake. Or in this case, a dust-free void. But there's a twist. Some dust-free supernovae do appear in dust-rich galaxies. That makes no sense on the surface. If the galaxy is full of dust, you'd expect its stars to follow suit. But these cases hint at something deeper. Maybe certain stars go through dust-clearing phases before they die. Maybe intense solar winds or magnetic storms blow away the outer layers in the final stages of life, stripping the dust-forming material before the explosion even begins. We've seen this in stars like Eta Carinae, massive, violent, and shedding matter like crazy. These stars can lose more than 90% of their mass before the final collapse. By the time they explode, there's almost nothing left to make dust with. It's like setting off fireworks in an empty parking lot. Bright, fast, loud, and gone in an instant. But here's the big question: why does this matter? It matters because dust isn't just an accessory in space. It's a storyteller. Dust carries the history of a star. It tells us what elements were there, what processes were active, and how the star lived and died. Without dust, we're flying blind. We lose a key part of the narrative. More than that, dust seeds new generations of stars. It cools gas clouds so they can collapse under gravity. It creates the raw materials for planets, comets, atmospheres, and maybe even biology. Without it, the cycle of star formation slows down. Entire regions of space can go quiet. So when we find dust-free supernovae, we're looking at systems that break the cycle. They explode, but they don't give back. They shine, but they don't seed. They die, but they don't create. It's like a one-way street in the universe: energy out, nothing in return. That has huge implications for galaxy evolution. Galaxies rely on a feedback loop. Stars form, stars die, they enrich the surroundings, and that triggers more stars. Dust is the medium that makes that loop efficient. Take it away, and the whole system sputters. Some simulations show that galaxies with lower dust production evolve differently. They form stars more slowly. They stay chemically primitive for longer. They have fewer planets, fewer complex molecules, and maybe fewer chances for life. They're like deserts in the sky, big, beautiful, and mostly empty. And again, we have to ask, are we in a rare oasis? Did we just happen to land in a galaxy, in a solar system, in a region of space, where the dust flowed at just the right time? Were our stars just dusty enough, just active enough, to give Earth its recipe? Because when you start connecting the dots, dust to molecules, molecules to oceans, oceans to life, it becomes clear how fragile the whole chain is. One missing link, and it all falls apart. That's why dust-free supernovae are such a big deal. Not because they're flashy, but because they might be the universe's dead ends, places where creation stops. Or maybe, just maybe, there's something else entirely. What if dust-free supernovae aren't just missing dust, but hiding it? Let's explore that next. What if the dust is there, but we simply can't see it? Think about this for a second. A supernova explodes with such incredible energy that it creates shockwaves, X-rays, gamma rays, neutrinos, basically a cosmic buffet of extreme phenomena. Now imagine that dust does form in the chaos, but instead of glowing or reflecting light like we expect, it becomes cold and dense. It clumps together so tightly, or it gets buried so deep inside the ejecta, that even our best telescopes can't pick it up. This isn't just a guess, it's a possibility that scientists are seriously considering. Cold dust emits in very long wavelengths, like those in the far infrared or submillimeter range. To detect that, you need specialized equipment like the Herschel Space Observatory, ALMA in Chile, or the James Webb Space Telescope. And even then, detection is hard. The signal is faint, buried under background noise, and only visible for a short period. So in some cases, what we call a dust-free supernova might actually be a dust-hidden one. There's even some precedent. SN 1987A, one of the most studied supernovae in modern history, didn't show much dust at first. But decades later, with better instruments, we found that it had quietly formed an enormous reservoir of cold dust, possibly enough to seed thousands of solar systems. The dust was there the whole time. We just weren't looking in the right way. And if that's true for SN 1987A, how many other supernovae have fooled us? It opens up a haunting idea. Maybe the cosmos is filled with silent dust clouds, leftovers of ancient explosions, just drifting in the dark, invisible to our eyes. They could be waiting, evolving, or maybe even colliding with other clouds, forming new structures, new stars, new chances for life. But then the mystery gets deeper. Because we've also observed the opposite. Some supernovae form what's known as dust echoes, bursts of infrared light reflected off existing dust far away from the explosion. These echoes can last months, even years, and give us a kind of map of the dust surrounding the blast. And yet, in dust-free supernovae, these echoes never appear. That suggests the surrounding space was already clean, either swept out by powerful stellar winds, or never rich in material to begin with. So now the puzzle has multiple layers. Not only is the supernova not producing dust, but it also isn't interacting with any. It's like lighting a match in a vacuum. Could this mean that some regions of space are fundamentally different? Maybe some parts of the universe, or some epochs in cosmic history, just didn't have the same conditions for dust creation. Maybe there were pockets of clean space, formed during the early days of galaxy formation, where the interstellar medium lacked the building blocks of dust entirely. If that's true, we may have stumbled upon a kind of cosmic boundary, zones where the physics of star formation, chemical enrichment, and even planetary evolution operated under different rules. And that would have serious consequences for how we understand the universe as a whole. See, our entire model of cosmic evolution depends on feedback loops. Stars produce heavy elements. Those elements form dust. Dust cools gas clouds. Gas clouds form stars. Over time, galaxies grow, mature, and diversify. But if dust-free supernovae are common, or more common than we thought, that loop breaks down. The early universe, for instance, likely had very little dust. The first stars, called population 3 stars, were massive, metal-poor, and lived short, explosive lives. If those stars mostly produced dust-free supernovae, it would delay the formation of later generations of stars and planets. It would mean the universe took longer to become complex. It would mean the emergence of life, anywhere, was pushed back by millions, maybe billions of years. Now take a step back and let that settle in. Dust-free supernovae might have delayed cosmic evolution itself. They might be the reason certain galaxies are sterile, why some regions of the universe remain chemically young, and why we don't see life everywhere we look. They might be the cosmic bottlenecks, choke points in the story of existence. But again, the mystery deepens. Because despite all this, we do see galaxies with plenty of dust, some so filled with it that they're called dusty starburst galaxies. These are places where star formation is happening at a frenzied pace, where new suns are being born by the thousands, where planets might already be forming in thick clouds of cosmic soot. And it's here, in these dusty galaxies, that we'd expect to see supernovae creating even more dust, feeding the loop, accelerating the cycle. But weirdly enough, some of the supernovae we've studied in these galaxies are still dust-free. Why? That contradiction is one of the most unsettling parts of the dust-free supernova mystery. It suggests there's a missing piece, a variable we haven't figured out yet. It might be related to magnetic fields. Strong magnetic fields can prevent dust grains from forming by disrupting the way molecules collide and bond. They can also channel the explosion in strange directions, blasting the material away before it has a chance to settle. It might be connected to rotation. Rapidly spinning stars can develop twisted, unstable outer layers that prevent dust from accumulating. In some cases, this leads to asymmetric explosions, blasts that don't move outward evenly, but instead spray material in wild, unpredictable ways. That can either destroy dust or bury it too deep to detect. Or maybe it has to do with neutrinos, the ghostly particles released in vast numbers during a supernova. We don't fully understand how neutrinos interact with matter, especially in the split-second chaos of a stellar collapse. If neutrinos can somehow affect dust formation, by altering temperatures or triggering phase changes, we'd be missing a major piece of the puzzle. And then there's the most unsettling theory of all. What if dust-free supernovae are the result of something unnatural? Now, this is speculative territory, but some physicists and astronomers have entertained the idea that certain stellar phenomena could be triggered by exotic particles, or even advanced technology. What if a supernova is being artificially manipulated, not to produce dust, but to avoid it? Maybe in some distant corner of the universe, a civilization has found a way to use supernovae as energy sources, propulsion systems, or even weapons. Maybe dust interferes with whatever they're trying to do, so they find ways to suppress it. Sound crazy? Sure. But think about it. Dust is messy. It blocks light. It gums up optics. It changes heat signatures. If you were trying to harness the power of a supernova, say, to power a Dyson sphere, or to drive a spacecraft across interstellar distances, you'd want that explosion to be as clean as possible. Dust would just get in the way. Again, this isn't a claim, it's just a question. But in a mystery this deep, every question counts. And that's what makes dust-free supernovae so fascinating. They aren't just an anomaly. They're a crack in the pattern, a clue that something about our universe is stranger than we thought. They challenge our assumptions about how stars die, how matter recycles, how galaxies evolve, and maybe even how life begins. And we're still only scratching the surface. Because the more we look, the more dust-free supernovae we find. And the more we find, the more we realize, we don't understand them at all. So now we're looking at a universe where dust-free supernovae might not be some rare exception. They might be happening more often than we ever thought, and we just weren't paying enough attention to them. In a way, that's terrifying. It means that a part of the cosmic machine we've been depending on to explain how everything builds and evolves might not be doing what we thought it was doing. And the implications don't stop at theory. They stretch into everything we think we know about cosmic time, galaxy growth, even why we exist in the first place. You see, we've always believed that dust is one of the fundamental pieces in the puzzle of how life happens. It's in the air we breathe, in the soil beneath our feet, in the clouds that rain water down. Every planet, every moon, every asteroid is, in some way, a byproduct of dust that came from a star that exploded. Our bodies, literally, are made of atoms that pass through clouds of interstellar dust. No dust means no clumping. No clumping means no planets. No planets means, well, no us. So when you start seeing supernovae that don't leave behind dust, it messes with everything. It's like trying to bake bread without flour. You're watching the oven heat up, you're seeing steam, you're smelling something cooking, but when you open the oven, there's nothing there. Just empty space. Astronomers have spent decades trying to explain it away. Maybe the dust is too cold to see. Maybe the light from the supernova is blasting it into gas before we can detect it. Maybe it never had the right ingredients to begin with. All valid possibilities. But none of them explain all the cases. Every time we think we've got it figured out, a new dust-free supernova pops up that breaks the rules. One of the weirdest things is how these dustless explosions show up in environments where we'd expect the opposite, in galaxies rich with heavy elements, where dust should be forming all the time. In fact, some of them happen right next to supernovae that do make dust. Same galaxy, similar mass, similar star types, completely different outcome. That inconsistency is what's freaking people out. Because it means we're missing a variable. Something we're not accounting for. Some unknown factor that flips the dust switch on or off, and we have no idea what it is. It could be something happening inside the star, deep in the core, long before the explosion even starts. Maybe some stars go through internal processes that change their chemical composition in ways we don't fully understand. Maybe they burn off the raw ingredients for dust before they even die, kind of like a chef running out of eggs before the cake goes in the oven. Or maybe it's something external. Maybe there's something in the star's environment, radiation, magnetic fields, nearby black holes, or even dark matter that changes the outcome after the explosion begins. Maybe dust forms, but then a jet of particles slices through it and blows it all away. Maybe a companion star nearby sucks the dust into itself before we can see it. We don't know. But here's a truly wild idea. What if some of these dust-free supernovae are not even the same kind of explosion we think they are? Let's rewind a bit. Supernovae come in a few different flavors. You've got Type I, where a white dwarf steals matter from a neighbor star until it can't take it anymore and detonates. You've got Type II, where a massive star runs out of fuel and collapses under its own weight. Then you've got Type IB and IC, which are kind of like Type II, but with certain layers of their outer shell missing. Now here's the thing, each of these types is expected to make dust in different ways. Some eject heavy elements slowly, letting dust grains form and clump up. Others blow everything out at once, too fast for dust to form. But every once in a while, we get an explosion that doesn't fit into any category. It behaves like a supernova in terms of brightness and energy, but the signature is off. The spectrum doesn't line up. The decay curve is strange. The afterglow fades too fast or lingers too long. And sometimes, just sometimes, these weird explosions also don't produce dust. So the question becomes, are we even looking at supernovae? Or are these something else entirely? Some astronomers have suggested that what we're seeing might be failed supernovae, stars that start to collapse, but instead of exploding, they just fizzle and vanish into a black hole. But the energy still escapes. The outer shell still gets ejected. We see a flash, but no bang. These could easily be mistaken for real supernovae. And if the collapse is fast enough, maybe there's no time for dust to form. Others think we might be witnessing collisions between stars, rare, high-speed smash-ups that send material flying in every direction. These events can look like supernovae too, especially if we catch them at the right angle. But again, the conditions might not be right for dust. Everything is moving too fast, too hot, too chaotic. And then there's the most chilling possibility. What if these are the final deaths of stars that lived in such alien environments that our physics doesn't apply? Imagine a star that formed in the early universe, long before galaxies looked like they do now. It grows up in a bubble of dark matter, far from any other stars. Its chemistry is strange. Its structure is unstable. And when it dies, it goes out in a way we've never seen before. No dust, no remnants, just a ripple of light across the void. If that's what we're seeing, then dust-free supernovae might not just be anomalies. They might be messages, relics from a forgotten age, hints of a time when the universe played by different rules. And this leads us to another question we can't ignore. What if our entire understanding of dust formation is wrong? We've built our models based on a few well-studied cases. But space is big. We're only seeing a tiny slice of it. There could be entire categories of stellar death out there that we've never observed. Maybe dust forms differently in different galaxies. Maybe it depends on local chemistry, or galactic evolution, or even the orientation of the explosion itself. What if, in some cases, the dust is simply delayed? That's a real theory, by the way. Some researchers think that in certain supernovae, the dust doesn't form right away. Instead, it takes years, even decades, for the ejected material to cool down enough for solid grains to start clumping. That means we could be labeling supernovae as dust-free, when really, they're just on a slow schedule. This was actually observed in SN 1987A, one of the closest and most studied supernovae ever. For the first few years, astronomers couldn't find any dust. It seemed like a classic dust-free supernova. But then, as the years passed, we started to see the signs. Cold dust. Huge amounts of it. Just late. That changes everything. It means we might need to watch these explosions for decades before we can really know what they're doing. And let's be real, most of the time, we don't have the resources or the patience for that. There are thousands of things happening in the sky every year. Supernovae fade fast. Telescope time is expensive. Scientists move on. So if the dust shows up 20 years later, we might miss it entirely. That means we might be wrong, not because the dust isn't there, but because we never stuck around long enough to see it. So now we're dealing with a whole spectrum of possibilities. Some dust-free supernovae might really be dust-free, no dust ever. Others might just be delayed. Some might have dust that's too cold or too thin to detect. Some might be happening in environments where dust can't survive. And others might not be supernovae at all. It's not a single mystery. It's a web of mysteries, all overlapping, all feeding into each other. And every time we look closer, we find another thread to pull. That's why astronomers are obsessed with this. It's not just about explaining one weird phenomenon. It's about rewriting how we understand stellar death, cosmic evolution, and maybe even the future of life itself. Because here's the final twist: if dust-free supernovae are real, common, and widespread, then there might be entire regions of the universe where dust never formed. No dust means no planets. No planets means no biospheres. No biospheres means no life. In other words, these supernovae might be the reason we haven't found anyone else out there. They might be the great silencers, cosmic events that sweep clean entire patches of the universe, making sure that nothing grows, nothing survives, nothing evolves. And if that's true, then somewhere out there, in the darkness between galaxies, the light from these explosions is still traveling. Still erasing. Still echoing. And we're just starting to see it. It's easy to assume that supernovae, these colossal, bright explosions, would always result in dust. After all, when a star reaches the end of its life, it sheds its outer layers, blowing out particles and creating what looks like a cosmic cloud. And that's true for many. But not all. Some supernovae break the rules. Some go off like fireworks, and leave nothing behind. No smoke. No trace of ash. No cosmic dust. Just an eerie, clean void where something cataclysmic once happened. These are what astronomers call dust-free supernovae. And they don't make sense. Not yet. Let's pause on that for a second, because when something in astronomy doesn't make sense, it usually means we're staring at something important. Something that might change what we think we know. Dust-free supernovae are important because they challenge our assumptions about how stars live and die. We thought that when massive stars exploded, they always produced dust. Dust, after all, is the building block of planets, of moons, of life. So when we see supernovae that don't produce dust, we have to ask, are we missing something huge? Maybe it's the timing. Astronomers have to act fast when a star explodes. The light from a supernova travels across millions, sometimes billions, of light years to reach us. And when we finally detect one, we're basically looking into the past. By the time we see the light, the star has already died long ago. So the moment of observation becomes everything. If dust forms later, weeks or months after the explosion, we might miss it entirely. But in the case of some of these dust-free events, astronomers kept watching, and still saw nothing. That's the mystery. No early dust. No late dust. No evidence that it ever existed. Some researchers have started wondering if the dust was never there to begin with, or if it somehow got destroyed in the blast. This gets more bizarre the more you think about it. If a star exploded, wouldn't it throw out everything? Elements, particles, clouds of debris? You'd expect a messy aftermath. Instead, these particular explosions clean up after themselves almost perfectly. Too perfectly. This makes some scientists think about the types of stars that cause these odd supernovae. Maybe we're not dealing with the usual suspects. Some believe these could be low metallicity stars, stars that don't have as many heavy elements inside them. Heavy elements are what form dust, so if the star didn't have much to begin with, it might not have much to throw out. But even that theory hits a wall. Because we've seen stars with very low metallicity still produce dust. Not a lot, but some. So why are these particular supernovae completely clean? Another theory dives into something a little more wild. Maybe the dust is there, but we can't see it. That sounds strange, right? But it happens. Dust can sometimes exist in forms that are practically invisible to our instruments. It could be extremely cold, or made of particles that don't reflect or absorb light in the way we expect. In a sense, it's like the cosmic equivalent of smoke that's only visible under ultraviolet light. If we're only looking in the wrong wavelengths, we might miss the dust entirely. But astronomers are getting smarter about that. They now use infrared, X-ray, and radio telescopes to see across the spectrum. And still, in some of these cases, they see nothing. And that leads to a bigger question: could these dust-free supernovae be hiding some entirely new kind of physics? Something we haven't accounted for? There's a radical idea floating around that some of these events might not be normal explosions at all. Maybe they're not even the result of a star dying, at least not in the way we understand death. Maybe they're the result of something exotic, like a failed supernova, where the star collapses into a black hole so quickly that very little matter escapes. Now that's spooky. Because in this scenario, the star dies not with a bang, but with a near-invisible implosion. All its mass falls inward. Gravity wins completely. And there's no outward explosion to spread dust. Instead, all that material gets trapped inside the black hole's event horizon. Nothing escapes. No light. No particles. No dust. What we're left with is the illusion of a supernova, but none of the leftovers. Just a silent graveyard in space. But let's not jump to black holes too fast. Some researchers are exploring another idea, that maybe magnetic fields are responsible. Magnetic fields around some dying stars can be unimaginably powerful, strong enough to bend matter, twist energy, and influence the shape of the explosion. If a supernova's magnetic field is strong enough, it might funnel most of the explosion into a narrow jet, leaving the surrounding space oddly clean. This wouldn't be the usual messy burst we expect. It'd be more like a surgical strike, clean, direct, and dust-free. There's also something else worth thinking about: the environment around the star. Maybe the star itself exploded like any other, producing dust, but the space around it was unusually empty. If the region of space was already cleared out before the explosion, there wouldn't be any material to collide with or stir up afterward. That might make it seem like no dust was created, even if it was. It's a possibility. But it doesn't fully solve the mystery. Because even in empty regions, the dust should be detectable. Yet in some of these dust-free events, it's like the universe pressed a delete key. Let's go deeper. There's a fascinating connection between dust and the way light behaves. When supernovae happen, the light they emit can get absorbed and scattered by dust. This is called extinction. It dims the light and changes its color. But when astronomers look at dust-free supernovae, they don't see this extinction effect. The light travels clean, bright, untouched. That's a smoking gun. It tells us not only is there no dust nearby, there wasn't any dust created in the explosion either. The light confirms it. And the more we learn about these events, the more questions we open up. What does this mean for the early universe? Back when the first stars exploded, long before our solar system existed, those explosions seeded the cosmos with dust. That dust eventually clumped into planets, moons, and life. If some stars exploded without making dust, could that change the story of how matter formed? Could entire regions of the universe have evolved differently because of a few quiet, dustless deaths? It's not just about missing dust. It's about the implications. If we don't understand why certain supernovae are dust-free, how can we be confident in our models of the universe's birth and growth? Every assumption we make about the cosmos builds on the idea that stars die in predictable ways. That explosions leave behind materials that build new things. Dust-free events poke holes in that model. They make us ask, what else don't we know? And if the dust is truly missing, not hidden, not transformed, but gone, that might point to something fundamental. Something deeper than supernovae. Something about how matter behaves under extreme pressure. How particles react to extreme temperatures. Maybe we're looking at physics that haven't been seen in labs. Maybe this is what it looks like when the universe plays by different rules. And here's another wild thought. What if the dust isn't gone, but was never formed in the first place because of quantum effects at the edge of the supernova. That's a very niche idea, but some theorists believe that when energy is released at extreme scales, particle formation might follow different paths. In those cases, atoms don't clump into molecules. Molecules don't clump into grains. And grains never form dust. It's like trying to bake a cake but the batter never thickens. That changes everything. We're going to keep pushing deeper into this, exploring the consequences of these eerie clean explosions, what they mean for black hole formation, and why they may be signs of entirely new kinds of stellar death. But for now, one of the most fascinating parts of this whole mystery is how much it's shaking up our understanding of the life cycle of matter in the universe. See, when a star explodes, it doesn't just end, it contributes. It gives back to the cosmos. All those heavy elements it forged in its core during its lifetime, things like iron, silicon, carbon, get blown out into space and become the raw material for the next generation of stars and planets. That cycle is essential. Without it, nothing we know could exist. No Earth. No people. No us. So when a supernova skips that step and leaves no dust, it's like tearing a page out of the universe's playbook. It throws a wrench into the recycling system of the cosmos. Let's talk numbers for a second. In a typical dusty supernova, scientists can observe up to a solar mass of dust, meaning the amount of dust expelled could weigh as much as our sun. That's a ridiculous amount of material. Now imagine an explosion of the same scale, but with almost none of that material left behind. It's like watching a building collapse and finding no rubble. That's how jarring these observations are. These aren't subtle differences. These are total contradictions of what we expect. Now you might be thinking, okay, but maybe there's some sort of cosmic cleanup going on. Like something erasing the dust before we can see it? That's a fair guess, and some scientists have wondered if something like radiation pressure could be so intense that it destroys dust grains almost instantly after they form. Imagine the blast from the explosion being so violent and hot that any potential dust gets vaporized on the spot. That's plausible, but there's a problem. If that were happening, we'd expect to see some kind of signature. A heat spike. A radiation trail. But in some cases, we don't. Instead, the aftermath is just empty. It's like the star was never there. This has led some astronomers to propose we might be looking at a class of supernova that doesn't behave like any we've studied before. These events might not be core collapse supernovae, the kind that usually comes from a massive star dying, but something more exotic. Something that involves compact objects like white dwarfs or neutron stars behaving unexpectedly. Maybe a white dwarf accretes mass, reaches a critical limit, and detonates, but under weird conditions where the material is burned so completely and cleanly that no dust survives. It's like a fire that leaves no ash. Let's talk about Type I supernovae for a second. These are usually caused when a white dwarf in a binary system steals material from its companion star until it explodes. They're incredibly important to astronomy because we use them as standard candles, predictable explosions we use to measure distances in the universe. But recently, astronomers have started seeing some Type I supernovae that are unusually faint or unusually clean. Could these be linked to the dust-free mystery? Maybe. Or maybe we've just been oversimplifying what Type I actually means. There's even a debate right now about whether some of these explosions should be called supernovae at all. Because some of them don't leave behind dust, or much debris, or even a clear remnant, there's a question of whether they belong in a new category entirely. Something like dark collapses, or invisible deaths. That might sound dramatic, but the cosmos doesn't care about our categories. It just does what it does. And if some stellar deaths are clean, quick, and silent, then maybe we've been looking for the wrong kind of evidence this whole time. This isn't just academic curiosity, by the way. The amount of dust in a galaxy affects everything, from how stars form, to how planets form, to how light from distant galaxies reaches us. If there are more dust-free events than we think, that means our models of galactic evolution might be wrong. Entire simulations of how galaxies grow and evolve are built on assumptions about how much dust stars create. So if that number is wrong, it means the simulations, and everything based on them, might be way off. Let's take a moment to think about what space would look like without dust. Right now, when we look at beautiful images from telescopes like Hubble or JWST, we often see glowing clouds of dust, nebulae, filaments, swirls of light and shadow. These aren't just pretty pictures, they're evidence of stellar activity. Dust traps light. Dust reflects it. Dust helps shape the look of galaxies. So a dust-free universe would look radically different. Sharper. Emptier. Maybe even colder. Without dust, space loses a lot of its texture. Now, here's a mind-bender. Could these dust-free explosions actually be telling us something about the universe's earliest moments? Think about it. The early universe had almost no heavy elements. Just hydrogen, helium, and a little lithium. So the first stars, called population 3 stars, would have died in ways that didn't create much dust, at least at first. Maybe what we're seeing in dust-free supernovae is a kind of echo of that era. Stars dying in a way that mimics how the very first stars died. If that's true, then every dust-free event is like a time machine. A glimpse back to the universe's childhood. This connects with another mystery. We've never directly observed a population 3 star. They're too old, too far away, and too short-lived. But we can observe their aftermath. And if dust-free supernovae are part of that aftermath, then we might be closer to understanding those ancient stars than we thought. Maybe we've already seen them die, we just didn't recognize what we were looking at. Let's go even further. What if, and this is a stretch, but bear with me, some of these dust-free explosions are not natural at all? What if they're evidence of something artificial? Some people have floated the idea that advanced civilizations might harness the energy of stars in ways we don't understand. Maybe they detonate stars as part of some massive engineering project, or even as a form of propulsion. It's wild speculation, sure. But if you saw a clean, dustless explosion in space, wouldn't you at least wonder? Back in the real world, astronomers are still hunting for more examples. The trouble is, dust-free supernovae are rare, or at least rarely identified. They often slip through the cracks because they don't match the templates astronomers use to classify explosions. If the light curve is weird, or if there's no dust detected, sometimes the event just gets tossed out as an anomaly. That's a problem. Because anomalies are often where the truth hides. We need to pay more attention to the things that don't fit. And in recent years, with new instruments coming online, like the Vera Rubin Observatory, we're going to be finding a lot more of these strange events. The Rubin telescope is designed to scan the entire sky rapidly, catching changes in brightness and movement. That means more supernovae, more data, more chances to spot the odd ones, the ones that don't behave, the ones with no dust. But it's not just about finding more of them. It's also about looking at them differently. That means studying the spectra in more detail, watching the light curves longer, measuring the surrounding space more carefully, and most importantly, being open to the idea that our current models might be missing something fundamental. Because maybe, just maybe, these dust-free supernovae are trying to tell us something we've been ignoring. We've peeled back some layers of this dust-free supernova mystery already, but there's still so much more under the surface. If you're still here, it means you're just as curious as the astronomers trying to make sense of what the universe is whispering through these strange explosions. Here's something we need to talk about: how these dust-free supernovae change our understanding of the cosmic dust budget. Yeah, it sounds boring. Cosmic dust budget. But this is one of the key building blocks for figuring out what the universe is made of and how it evolves. Galaxies aren't just made up of stars and gas. Dust plays a vital role in cooling gas clouds, which allows them to collapse and form new stars. If there's a shortfall in the expected amount of dust, that has massive implications for star formation models. So if more stars are dying without leaving behind the usual dusty remains, then maybe the dust budget we've been estimating is just wrong. And that throws off everything built on top of it. This leads to a critical follow-up question. Are these dust-free events new, or have we just not noticed them before? That's huge. Because if they've always been happening and we've just misclassified or ignored them, then a major piece of the puzzle has been sitting in plain sight. It wouldn't be the first time. Science is full of examples where we looked at something for years and misunderstood it because we didn't have the right framework. Like when people thought the sun revolved around Earth, or when Pluto was considered a planet. Maybe we've been seeing these supernovae for decades and simply thought they were oddball versions of something else. One possibility is that we haven't had the right kind of instruments to really catch what's going on. Many older telescopes weren't equipped to see the wavelengths where dust shows up, especially in the infrared spectrum. That's where dust emits most of its heat. With new telescopes like the James Webb Space Telescope, which specializes in infrared, we're finally seeing these events in ways we couldn't before. And sometimes, what we're seeing is nothing. No dust. That's not just surprising, it's alarming. Because when Webb sees a star explode and the space around it remains eerily clean, that's not just a scientific note, that's a cosmic question mark. It forces astronomers to ask, what kind of physics are we missing? What law isn't working the way we thought? These are not casual questions. These are rewrite the textbooks kinds of questions. And they don't come along very often. Here's another curveball. Location matters. Some of these dust-free supernovae seem to happen in parts of galaxies that are already low in dust and metals. That kind of makes sense. If a star forms in a low-metal environment, maybe it doesn't have much to contribute when it dies. But then there are other cases where dust-free explosions are seen in rich, metal-heavy regions, places where you'd expect the exact opposite. That contradiction points to something deeper going on, something that can't be explained by environment alone. It suggests that whatever's causing the dust to vanish is happening inside the star itself, or during the explosion, not just outside. So what's the process inside the star that might cause this? One idea is that the fusion process in these particular stars goes a little differently. Maybe the fusion burns cleaner, more efficient, less waste. If the final stages before collapse are hotter or denser than normal, they might destroy dust-forming molecules before they ever make it out into space. That would explain the lack of dust. But again, we should see some signature of that extreme process, and in many cases, we don't. It's almost too clean. Suspiciously clean. Let's talk about one of the most mind-blowing theories floating around. The possibility that some stars collapse directly into black holes without even exploding. These are sometimes called failed supernovae. They don't light up the sky. They don't create much of a show. They just vanish. If a massive star dies and forms a black hole without a traditional supernova, that would explain the lack of dust, because there's no explosion to fling the dust outward. Some astronomers think we might have already witnessed this happening. A star just disappears from our sky, and nothing is left behind. Creepy, right? If failed supernovae are common, then the whole concept of what happens when stars die needs to be rewritten. We've always assumed that the biggest, brightest stars go out with the biggest, brightest bangs. But maybe that's not true. Maybe some of the most massive stars just collapse silently, pulling everything, even their own potential dust, into the black hole they leave behind. That's not just unsettling, it's disruptive. Because it means we're missing a big part of how matter cycles through the universe. But here's another twist. Maybe some of the dust is being created, just much farther away than we expect. In a typical supernova, dust forms in the cooling outer layers of the exploded star. But in these dust-free cases, maybe the dust gets pushed out so far, and so quickly, that we're not even looking in the right place to find it. By the time we start our observations, the dust could be tens of billions of kilometers away, diluted and too faint to detect. It's like a magician's sleight of hand. The dust is there, but it's not where we're looking. This leads to a strange possibility. We might be underestimating how fast and far supernova ejecta can travel. If the explosion is unusually energetic, or if the geometry of the blast focuses material in narrow jets, then the dust might be ejected in a way that makes it almost invisible to us. Picture a firework that shoots out in a tight, directional burst instead of a wide, glowing cloud. If you're standing in the wrong place, you might not see anything at all. And then there's the issue of timing. Dust doesn't form instantly after a supernova. It takes time. Sometimes months or even years. So if our observations are limited to the first few weeks after the explosion, we might miss the dust completely. This is especially true for telescopes that only monitor a portion of the sky or that only check back on supernovae occasionally. We could be seeing the before picture but not the after. That's a huge blind spot. But here's where it gets weird again. Even in long-term observations of certain events, the dust still doesn't show up. Not after a year. Not after 2. Nothing. That kind of result sends scientists back to the drawing board. Because now it's not just about missing the window. It's about the dust genuinely never forming. That's rare. And disturbing. Let's loop in the idea of quantum processes for a moment. Some theorists have speculated that certain high-energy environments, like those in exotic supernovae, might actually prevent the formation of dust through quantum interference effects. It's a fringe idea, but it's interesting. If the particles that would normally come together to form dust are being kept apart by high-energy quantum fluctuations, then maybe the dust is being stopped before it even starts. That would be a completely new process, something we've never seen happen on that scale before. Now think about how all of this ties into the cosmic infrared background. That's the collective glow of all the dust in the universe, spread across time and space. Astronomers use it to estimate how many stars have lived and died. If dust-free supernovae are more common than we think, then our estimates for how many stars have died in the universe might be totally wrong. Maybe the universe is darker than we realize. That's unsettling on a deep level. And we haven't even scratched the surface of how this mystery could impact our understanding of cosmic reionization, the period in the early universe when the first stars lit up and reionized the gas between galaxies. Dust plays a role in how radiation travels. If early stars died without creating dust, then light would have traveled differently. That changes how we interpret observations from the very earliest times. So let's step back for a moment. What started as a weird quirk, a supernova with no dust, has snowballed into a full-blown crisis of understanding. This isn't just about explosions. This is about the life cycles of stars, the structure of galaxies, the origin of elements, and the fate of the cosmos itself. It's about realizing that the universe is still keeping secrets from us. And maybe it always will. Let's dive deeper into the implications and mysteries swirling around these dust-free supernovae. What we're dealing with is not just a curiosity. It's a growing body of evidence that suggests the death of stars may be far more varied, complex, and perhaps even stranger than our models have dared to imagine. Let's begin by revisiting the core contradiction. Stars, by their very nature, are factories of dust and heavy elements. When they explode, they scatter these materials across the cosmos, seeding future star systems and even forming the basic components of planets and life. So when a supernova leaves no visible trace of dust behind, it's like watching a tree fall and finding no leaves, no branches, no splinters, nothing. It challenges the foundational assumption that stellar death is always a process of creation, not just destruction. This brings us to one of the most provocative ideas in current astrophysics: differential element production. What if certain stars, under very specific conditions, fuse elements in such a way that the end result is more exotic and less dusty than expected? Instead of carbon-rich molecules that can form soot and silicates, maybe these stars end up dominated by lighter or more volatile compounds that dissipate quickly or are simply invisible to our detectors. That would mean the chemical fingerprint of their explosions would be fundamentally different. And that naturally connects to another theory: magnetorotational supernovae. These are extremely rare and exotic explosions where the star's intense magnetic field and rapid rotation combine to produce a highly energetic, narrowly collimated jet-like explosion. These events might produce very little dust because they channel most of the energy and matter into narrow beams, ejecting elements at such speeds and directions that the typical dusty envelope never forms. If dust needs a dense, cooling environment to condense, then such a focused and fast outflow could prevent that from happening entirely. The fact that some of these dust-free supernovae have been seen in early type galaxies, those that are older, more stable, and less dusty themselves, only deepens the puzzle. These galaxies should be long past their peak star formation days. Yet we find new supernovae happening there, and some of them are unexpectedly dustless. Are we witnessing the deaths of unusual, long-lived stars? Or are these galaxies hiding remnants of past mergers that triggered a new burst of star formation long after their supposed retirement? There's also the idea of gravitational lensing magnification. Sometimes, the light from a distant supernova gets bent and magnified by a foreground galaxy, allowing us to see explosions we wouldn't otherwise detect. If some of the dust-free supernovae are actually ultra-distant events amplified in this way, then we might be getting a skewed sample of the universe, biased toward the brighter, more unusual explosions that just happen to line up perfectly with gravitational lenses. And this brings us to a more speculative frontier: dark matter interactions. Some physicists have floated the hypothesis that dark matter might play a role in the later stages of stellar evolution, especially in the cores of massive stars. If dark matter somehow accumulates in a star's center, it could alter the final collapse, changing the explosion dynamics in ways we can't yet model. Perhaps these altered collapses suppress dust formation. Or perhaps they create new, invisible forms of matter that escape detection altogether. This connects with another disturbing possibility: the dust is there, but we can't see it because it's made of exotic compounds. Our telescopes are tuned to detect specific wavelengths, usually those associated with carbon, silicon, and oxygen-based dust. But what if some of these supernovae are creating dust out of elements that absorb and emit in completely different parts of the spectrum? We might be blind to entire clouds of strange, cold matter simply because we never thought to look for them. Here's where the role of neutrino detection becomes crucial. Supernovae produce floods of neutrinos, nearly massless particles that rarely interact with anything. Tracking neutrino bursts can help us spot hidden supernovae, even if their visible or dusty signatures are missing. Recent advancements in neutrino observatories like Candy and IceCube are giving scientists new tools to hunt for these otherwise invisible explosions, potentially confirming that dustless events are more common than assumed. One more direction this mystery could point us toward is the multiverse hypothesis. If certain fundamental constants, like the strength of gravity or the charge of the electron, are slightly different in other regions of a greater multiversal landscape, then it's possible that some stars form and die under very different physical laws. Could some of these dust-free supernovae be bleeding across from adjacent branes or dimensions? It's a wild idea, but some astrophysicists have proposed that unexplained anomalies like this might be evidence of deeper structure in the cosmos. We also have to think about the sociological side of science. For decades, the models we used to understand supernovae were based on the limited data we had. Many studies focused only on the bright, dusty events, because that's what was easiest to see. The fainter, weirder ones? They got ignored. Only now, with the power of automated sky surveys and machine learning algorithms that can sift through mountains of data, are we catching glimpses of the outliers. The more we look, the more it seems like the universe isn't weird in a few places. It might be weird everywhere. That brings us to a psychological crossroads for astronomy. Are we ready to accept that our neat categories, Type 1, Type 2, with dust, without dust, might be misleading simplifications? Maybe every star's death is a custom-tailored event, influenced by dozens of subtle variables we don't yet fully understand: mass, rotation, binarity, magnetic fields, metallicity, even position in a galaxy. So what do we do next? One answer lies in long-term monitoring. Projects like the Vera-C, Rubin Observatory's Legacy Survey of Space and Time, LSST, are going to revolutionize how we watch the sky. With near-nightly images of the entire southern hemisphere, we'll have unprecedented data on how supernovae evolve over months and years. We'll finally be able to see whether dust forms late, or never forms at all. In parallel, missions like JWST will allow us to peer deeper into the infrared spectrum than ever before. We'll be able to study the temperature, structure, and composition of supernova remnants with a precision that simply wasn't possible a decade ago. Combined with radio and X-ray telescopes, we'll start to piece together a full spectrum view of each explosion. And maybe, just maybe, we'll find that these dust-free supernovae are pointing us toward a deeper cosmic truth. That the universe isn't just stranger than we know. It's stranger than we can know. Let's keep going and dive even deeper into the bizarre and mind-bending possibilities that dust-free supernovae unlock. The fact that we can even use the term dust-free when talking about an event as chaotic and powerful as a star exploding is already strange. But it only gets stranger when you think about how much this challenges what we thought we understood, not just about supernovae themselves, but about how the entire cosmos is shaped and evolved. Let's start with the ripple effect. If more supernovae than we expected turn out to be dust-free, then that throws off our models for how galaxies evolve. Dust isn't just some leftover mess after a star dies, it's fuel. Dust cools interstellar gas, helps form new stars, clumps into planets, and is a critical ingredient in the chemistry of life. Without it, galaxies would be dry, sterile places. So if a significant number of supernovae aren't producing dust, then maybe the universe has fewer raw ingredients for future stars than we thought. That could mean that some galaxies evolve slower, or that star formation rates are lower in regions where these unusual explosions dominate. Then there's the fact that these dust-free events may not be as rare as once assumed. For decades, we only saw the flashy supernovae, the bright, dusty ones, because they stood out in the night sky. Our instruments were simply not sensitive enough to catch the fainter or stranger ones. But now, with advanced telescopes scanning the sky every night, we're spotting things we've never seen before. And what we're learning is that the normal explosions might not be normal at all. They're just the easiest to see. Now imagine this. What if our entire understanding of the life cycle of matter in the universe is based on a biased sample? It's like trying to understand human history by only reading celebrity gossip columns. You'd miss out on everything that wasn't loud and showy. That's what's happening in astronomy. Until now, we've only seen the cosmic explosions that shouted the loudest. This brings up a huge philosophical problem. What else are we missing? If dust-free supernovae were right there all along, hidden in plain sight, what other invisible phenomena are shaping the universe in ways we haven't even imagined yet? Are there whole classes of stars or galaxies or cosmic events that don't emit in light, or dust, or radio waves, and we've just never noticed them? Could dark stars exist? Objects so faint and dustless and cold that they're only detectable through gravitational waves or subtle effects on nearby objects? It also makes us wonder, what happens after a dust-free supernova? In a typical explosion, you're left with a glowing cloud of gas and dust that we can track for years. But in these strange cases, the aftermath fades quickly. That makes it harder to find remnants, harder to study the neutron star or black hole that's left behind, and harder to understand the full process of what just happened. It's like trying to solve a crime without a body, no fingerprints, and no witnesses. This leads us to an even weirder idea. What if some dust-free supernovae are actually part of a totally different class of event? Maybe not all of them are traditional core collapse supernovae. Some could be what's known as failed supernovae, where a massive star collapses directly into a black hole with little or no explosion at all. In some cases, we've seen stars simply vanish from our sky, and all that's left is a quiet spot. No boom, no light show, just gone. And maybe what we've been calling dust-free supernovae are actually these failed explosions with just enough energy to emit a flash of light, but not enough to throw out dust or gas. There's even the possibility that some of these events are triggered by exotic physics, things like quark deconfinement, where the core of the star reaches such a high density that protons and neutrons break down into a soup of quarks. That kind of reaction might release huge amounts of energy in ways we don't yet understand, and could leave behind a strange remnant like a quark star or some other exotic form of matter. If that kind of collapse doesn't follow the typical rules, it might explain why no dust is formed. And let's not ignore the role of binary systems, two stars orbiting each other in a close dance. A surprising number of stars live with partners, and when one explodes, the interaction can be wildly complex. Maybe the companion star strips off outer layers before the explosion. Or maybe the explosion itself is altered by the gravitational dynamics of the pair. If a lot of the mass is pulled away or accelerated before dust can form, you're left with a clean supernova that fades quickly, without leaving dust behind. Another mind-bending idea? Supernova imposters. These are events that look like supernovae at first glance but turn out to be something else entirely, like a massive star ejecting part of its outer shell in a huge flare-up, but not dying completely. Some of these outbursts are powerful enough to mimic the early light of a supernova, but because the star survives, they don't produce the same aftermath, and the dust signatures are totally different. Maybe some of our dust-free supernovae are actually imposters, bursts of energy that fooled us into thinking something died when it didn't. And yet another possibility? We're seeing supernovae from a different angle. A single explosion might look very different depending on where we're standing. If dust is ejected in a disk or a cone, and we're looking at it from a direction where little or no dust is along our line of sight, we might think it's dust-free, even though from another angle, it would look normal. That means some of the mystery might be due to perspective. But the only way to test that is with multi-angle, multi-wavelength observations of many supernovae over time. We also need to think about the role of metallicity. That's the amount of elements heavier than hydrogen and helium in a star. Stars with low metallicity, often older or more distant stars, may not produce the same kinds of dust as younger, metal-rich ones. And if the dust can't form, or if it forms more slowly, that could explain what we're seeing. This ties into the evolution of galaxies over cosmic time. Early stars may have died differently, and their explosions might not match what we're used to seeing in the modern universe. Another important angle is host galaxy environment. The surrounding material plays a huge role in how a supernova behaves. If the environment is dense, the explosion can crash into nearby gas and generate extra heat and light. If it's empty, the explosion might fade quickly and seem much less dramatic. A dust-free supernova might be the result of an unusually clean environment, where there simply wasn't any material nearby to heat up or to form visible dust afterward. It's also worth noting that observational bias could be fooling us. We tend to point our best telescopes at galaxies that are already interesting, spirals, mergers, galaxies with lots of star formation. That might skew our data towards certain kinds of explosions. But with all-sky surveys becoming more common, we're finally starting to collect a more random, less biased sample of supernovae. That's why we're only now discovering just how weird and varied they can be. Some researchers even speculate that dust-free supernovae might be tied to primordial stars, the very first generation of stars, formed when the universe was still young and made mostly of hydrogen and helium. These stars would have had virtually no metals, and when they died, their explosions might look totally different from modern supernovae. Maybe what we're seeing is the rare death of ancient stars that somehow survived into the present day. And there's the possibility that the dust is there, but in a form we can't detect yet. Maybe it's incredibly cold, or made of unfamiliar compounds, or hidden in wavelengths we don't usually observe. Our instruments are powerful, but they're not perfect. We might be staring right at the evidence, and not even realizing it. The mystery of dust-free supernovae isn't just a curiosity. It's a crack in the wall of what we thought we knew. And every time we peer through that crack, we get a glimpse of a universe that's not just vast, but filled with secrets we're only beginning to understand. Let's continue peeling back the cosmic curtain on dust-free supernovae. Because this mystery isn't just about dust, it's about everything we thought we knew about how stars live, die, and reshape the universe. What happens when a star doesn't follow the rules we've written for it? The answer might unravel more than stellar models. It could rewrite entire chapters of cosmology, galactic evolution, and even planetary formation. Let's begin with something strange. Dust isn't just residue, it's memory. When a star explodes, the dust that forms in the aftermath carries the chemical fingerprints of that star's final moments. Scientists use this dust to decode what happened inside the star before and during the explosion. But when there's no dust, there's no record. It's as if a library burned down and left no ashes. All the rich detail of the star's death, its temperature, its pressure, its composition, is lost to us. These dust-free events become blank spots in the historical record of the cosmos. Now think about the consequences for planetary systems. Dust is the beginning of planets. Every rocky planet, every asteroid, every grain of sand you've ever touched comes from stardust. When supernovae don't produce dust, it changes the balance of matter available for the next generation of stars and planets. In regions of space where dust-free supernovae dominate, the building blocks of Earth-like planets might simply not exist. This has huge implications for the search for life in the universe. Because no dust means no rocky worlds, no oceans, no biospheres. Some astronomers are starting to ask a radical question. Could there be galaxies without any rocky planets at all? Imagine galaxies filled with stars but devoid of dust, no clouds of gas to collapse into new stars, no disks of debris forming planets. Just vast, sterile stretches of space where stars are born and die cleanly, silently, and without legacy. If such galaxies exist, they could be invisible to our telescopes, dark, cold, and untraceable in most wavelengths. And if we've missed them because of our focus on luminous, dusty galaxies, we may have fundamentally misunderstood what the universe looks like on large scales. Another eerie question follows. What if we're wrong about how much matter is even out there? For decades, we've estimated the amount of baryonic, normal, matter in the universe based in part on how much dust we see. But if a whole category of explosions doesn't leave dust behind, then our numbers could be skewed. We might be missing huge chunks of matter, undetectable by our current tools, because they're not lighting up the sky in the ways we expect. And let's dive into an even stranger scenario. What if these dust-free supernovae are signatures of advanced civilizations? This may sound like science fiction, but consider the idea seriously. If a highly advanced species wanted to harness the energy of a star, they might trigger a controlled stellar collapse to extract energy, or manipulate spacetime. A clean, dust-free explosion would minimize waste and limit detectable emissions. It would be, in essence, a technological supernova, engineered for precision. While there is no evidence to support this yet, the mere possibility pushes our imagination into realms where astrophysics meets astrobiology and technosignatures. Let's bring it back to physics. One key idea is that some dust-free explosions may result from ultra-stripped supernovae. These occur in binary systems where a companion star has already peeled away most of the supernova progenitor's outer layers before it dies. What's left is a bare, dense core that explodes with just enough force to leave a neutron star behind, but not enough to generate the usual fireworks. These kinds of events are thought to be common in the formation of double neutron star systems, the very systems responsible for kilonovae and gravitational wave events. If dust-free supernovae are actually part of the chain of events that lead to gravitational wave sources, they're far more important than we thought. Speaking of gravitational waves, there's a chilling idea. Some of these dust-free events might be precursors to invisible catastrophes. If a neutron star left behind by a dust-free supernova later merges with another object, a black hole, another neutron star, we might detect only the merger via gravitational waves, never realizing that the original explosion was dustless and undetected. This raises the question, how many of the gravitational wave events we see today were born from invisible stellar deaths centuries or millennia ago? There's also a tension forming in the field. The more we study, the less we agree. Different teams observing similar supernovae report wildly different findings. Some see faint traces of dust, others see none. Some suggest exotic physics, others say we just need better instruments. The lack of consensus itself is a clue that we're staring into a problem deeper than any single model. It's not just a new kind of star, it's a challenge to the way we do science. And let's not forget how this mystery touches on time itself. Many of these dust-free supernovae fade faster than expected, suggesting that their internal processes are quicker, sharper, more abrupt. The light curves, graphs showing how the brightness changes, don't match any known category. This rapid fading may indicate smaller amounts of radioactive nickel, or different internal structures in the exploding star. But it also means we might be missing many of them entirely, simply because they're gone before our telescopes catch them. Then there's the magnetar connection. A magnetar is a type of neutron star with an insanely strong magnetic field, billions of times stronger than anything on Earth. Some dust-free supernovae may be producing magnetars as their end state. These powerful remnants can release intense X-rays and gamma rays, and may be linked to phenomena like fast radio bursts, FRBs. If that connection is real, dust-free supernovae might be the seeds of some of the strangest signals we've ever detected from deep space. Another possibility: the dust never forms because the explosion is too hot, too fast, too violent. Dust needs relatively cool, dense conditions to condense out of gas. If the supernova explodes with too much energy, or expels its material at ultra-high speeds, there might be no chance for dust grains to coalesce before everything is too spread out. This ties back into the energy budget of the star. If certain types of core collapse are just too efficient, they leave no leftovers. Let's pivot slightly and consider the cultural impact. Every time we revise our understanding of how stars die, it affects how we view ourselves. We come from stars, not metaphorically, but literally. The carbon in our bodies, the iron in our blood, the oxygen we breathe, it all came from explosions. When we find that some stars die without leaving behind these elements in the same way, it raises questions about the conditions that led to us. Were we lucky to be born in a region of the galaxy rich in dusty supernovae? Would we even exist if the explosions around us had been clean? On the scale of the universe, dust-free supernovae might turn out to be exceptional or foundational. We don't yet know. But the implications ripple out into nearly every field: particle physics, cosmology, planetary science, astrobiology. These silent, disappearing stars might hold the keys to understanding dark matter, dark energy, or the earliest moments of cosmic evolution. And maybe the greatest mystery of all is this: what don't we know that we don't know? Every new discovery like this reminds us that our view of the cosmos is still partial, still flawed, still shaped by what our instruments can detect, and what our minds can imagine. Dust-free supernovae are the cosmic equivalent of a whisper in a noisy room, and now that we've started to hear them, we may never see the universe the same way again. Let's dive deeper into what dust-free supernovae could tell us about the architecture of the universe. Because if stars are dying without producing dust, then we have to reconsider how galaxies evolve, not just in the long run, but from their very beginnings. Galaxies are shaped by the life cycles of their stars. The explosions seed the environment with heavy elements. Those elements cool the surrounding gas, allowing it to collapse into new stars. But without dust, the cycle stalls. So we have to ask, how many galaxies have had their star formation stunted or altered by the dominance of these clean explosions? This leads to a bigger question: could dust-free regions of space be more common than we thought? Telescopes are biased toward what's bright, what reflects or emits light in visible or infrared wavelengths. Dust is excellent at absorbing and re-radiating energy, especially in the infrared. If a region of space lacks dust, it might be cold, dim, and nearly invisible to the instruments we rely on most. These could be entire, quiet zones in the cosmos, real places, vast in scale, that we've simply overlooked. Not because they don't exist, but because they're not broadcasting the usual signals. Now think about this. Dust plays a massive role in how light travels through the universe. It scatters, dims, and colors the light we see from distant stars and galaxies. Astronomers often have to correct for dust extinction when measuring light. But what if some of the data we've corrected was never dusty in the first place? What if we've been interpreting clean signals as ones that were affected by dust? That would throw off distance calculations, brightness estimates, and even our measurements of the expansion of the universe. Dust-free supernovae aren't just astrophysical curiosities. They could be hiding in the margins of our data, subtly changing how we see everything. And there's something strange about how hard they are to classify. When a new supernova is spotted, astronomers quickly rush to assign it to a type IA, Type II, Type IB, and so on. These categories depend on the elements visible in the spectrum, how fast the explosion fades, how bright it gets. But dust-free supernovae often don't fit neatly into any box. Some have odd light curves, others have weak or missing hydrogen lines. some seem too dim for the amount of energy they release. It's like trying to sort puzzle pieces from a different set entirely. This has led some to propose entirely new categories: transitional supernovae, fast-evolving luminous transients, felts, or calcium-rich gap transients. Many of these have one thing in common: a lack of dust in their surroundings. They erupt quickly, fade quickly, and leave behind little to no material. Some might not even come from stars like our Sun. They could come from white dwarfs stealing mass in binary systems, or from stars that have been stripped to their core by gravitational forces. Speaking of stripped stars, there's growing evidence that many dust-free supernovae come from binary systems. When a star orbits a close companion, that companion can siphon off its outer layers. This creates what's called an ultra-stripped core, a star that's lost its hydrogen and helium envelopes. When it explodes, there's less material to interact with the shockwave, and so the whole process is quieter, faster, and cleaner. These are perfect candidates for dust-free events. But it means we're not just studying single stars anymore. We're talking about complex dance routines between stellar pairs. Let's zoom out again. If more stars are exploding in this clean, fast way, then the overall timeline of chemical enrichment in galaxies could be very different. Dust doesn't just form planets, it shields molecular clouds from radiation, allowing them to collapse and form new stars. Without dust, there's less shielding. Star formation may slow down, or the stars that do form may be different in size and composition. Entire epochs of galactic evolution could be different in regions dominated by dust-free explosions. And here's another dimension: the effect on black hole formation. If dust-free supernovae are more common among very massive stars, or ultra-stripped stars, then the process by which black holes form might be more widespread than we thought. A cleaner explosion could allow more mass to collapse inward, making the black hole heavier. Over cosmic time, this changes the distribution of black holes. And when those black holes collide, producing gravitational waves, their origins may trace back to explosions we never even noticed. Now take this a step further. Some researchers suggest that certain dust-free events might not be supernovae at all, at least not in the traditional sense. Instead, they could be failed supernovae. This is where a massive star collapses inward but doesn't produce a bright explosion. Instead, it quietly becomes a black hole, with only a faint flicker of light, or none at all. These silent deaths would be nearly impossible to detect, unless we catch them at just the right moment. Dust-free explosions may be the visible tip of an iceberg of quiet stellar collapses. This raises fascinating possibilities for the dark matter mystery. If large numbers of stars are dying without visible signatures, leaving behind compact remnants like black holes or neutron stars, then they could be contributing mass to galaxies that we haven't accounted for. Some theorists have even proposed that a fraction of dark matter could be made up of primordial or undetected black holes. Dust-free stellar deaths could be quietly inflating the invisible mass budget of the cosmos. And we're not done yet. Let's go back to the magnetar theory. Some dust-free supernovae seem to leave behind neutron stars with extreme spin rates and magnetic fields. These objects, magnetars, might be responsible for fast radio bursts, FRBs, those millisecond-long pulses of energy that appear randomly across the sky. If the birth of a magnetar is linked to a dust-free supernova, then we may be seeing the final and first breath of a cosmic monster, its death as a star and its birth as a pulsing, magnetic core. Now here's something really strange: time dilation. Because of how fast and faint these events are, many dust-free supernovae might look totally different depending on when and where you observe them. A distant, fast-fading event might be redshifted and stretched in time, making it blend into the background noise of the sky. We might already have the data for dozens of dust-free explosions, but they're buried in the archives, unrecognized because their signatures don't match our expectations. And there's the possibility that these events could be the missing links in understanding gamma-ray bursts, GRBs. Some GRBs are linked to supernovae, but not all. Dust-free explosions could be part of the explanation. A clean, powerful jet-driven explosion could punch through the outer layers of a stripped star, creating a burst of gamma rays without much leftover debris. These naked, Explosions would be hard to trace back unless we catch the gamma-ray signal in real time. Let's not forget the role of metallicity. A star's metal content influences how it lives and dies. Stars in metal-poor environments, like the early universe, may be more likely to explode in dust-free ways. That means dust-free supernovae might not just be local oddities. They could be fossils of the earliest generations of stars. And if so, they might help us finally understand what happened in the first billion years after the Big Bang, when the universe transitioned from dark, empty space to the rich structure we see today. So now we're not just talking about an anomaly, we're talking about a potential key to cosmic history. A thread that ties together star formation, planet formation, galactic evolution, gravitational waves, dark matter, and even the structure of the early universe. That's the kind of mystery that doesn't just demand answers, it reshapes the questions. Dust-free supernovae may at first seem like a niche, rare event, but the more we learn, the more they seem like a natural part of the cosmic ecosystem, hidden in plain sight. Their subtlety challenges our assumptions about how the universe recycles matter and energy. One of the fascinating things about dust-free supernovae is how they could help solve the mystery of why some supernova remnants look so different from others. Usually, when a star explodes, it leaves behind a glowing nebula rich in heavy elements and dust. But astronomers have spotted remnants that appear unusually clean, almost like the star exploded in a vacuum with little leftover material. These remnants are puzzling because they don't fit neatly into the classic supernova models. Dust-free explosions provide a neat explanation. The star lost most of its outer layers before going supernova, leaving very little material to form dust. It's like peeling an onion. The outer layers of a star are where most of the dust-forming elements are created during the explosion. If those layers have been stripped away, there's less raw material left to produce dust after the blast. But that stripping process isn't simple. It often involves complex interactions with a companion star, or strong stellar winds that blow the outer layers into space over millions of years. Understanding how these stripped stars evolve is a frontier in astrophysics, bridging stellar evolution with supernova physics. And when a supernova doesn't make dust, it changes how it interacts with the surrounding space. Dust normally acts like a cosmic sponge, soaking up energy and re-radiating it in infrared light. Without dust, the energy from the explosion is released differently, often making the supernova appear dimmer in infrared and brighter in visible or ultraviolet light. This difference impacts how we detect and classify supernovae. Some dust-free events might have been missed simply because they shine in wavelengths our telescopes weren't looking for. Then there's the question of cosmic dust itself. Dust is everywhere, floating in interstellar space, blocking and scattering light, and even influencing the formation of molecules. If dust-free supernovae produce less dust, that means the overall dust budget in a galaxy can be altered significantly. Since dust helps cool gas clouds and form stars, a shortage could slow down star formation or change the kinds of stars that form. This might help explain why some galaxies appear less active, or why some star-forming regions seem sterile compared to others. Dust-free supernovae also invite us to reconsider the life cycle of massive stars. In a dusty explosion, a large amount of mass is expelled, enriching the galaxy and triggering new star formation. But with dust-free explosions, more mass might be swallowed by the collapsing core, leading to the formation of heavier neutron stars or black holes. This means dust-free supernovae could be one of the pathways for creating the most massive black holes we observe. This ties directly into gravitational wave astronomy, a new window on the universe. When two black holes merge, they release ripples in spacetime that we can now detect. But the origins of those black holes, how massive they are, where they come from, remain a hot topic. Dust-free supernovae, by producing more massive remnants, might explain some of the heavy black holes detected by LIGO and Virgo detectors. These events could be the hidden factories of the universe's most exotic objects. The magnetic fields left behind are equally intriguing. Dust-free supernovae sometimes produce magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. Magnetars are mysterious objects capable of generating enormous bursts of energy. Their formation through dust-free explosions suggests these supernovae aren't just quiet endings. They can be violent births of new, extreme cosmic phenomena. Another curious angle is the connection to fast radio bursts, FRBs. These millisecond pulses of radio waves come from unknown sources, and magnetars formed in dust-free supernovae have been proposed as one likely cause. This connection opens up a whole new way to study the aftermath of dust-free explosions by observing FRBs across the universe. And what about the cosmic timeline? Dust-free supernovae might have been more common in the early universe. Back then, the first stars formed from nearly pure hydrogen and helium, with almost no metals, elements heavier than helium. Metal-poor stars have weaker winds and might lose their envelopes differently, favoring dust-free explosions. If so, dust-free supernovae could be relics of the universe's infancy, offering clues about the first generations of stars and how they shaped everything that followed. This leads to another mind-bending thought. If dust-free supernovae were common in the early universe, then the buildup of dust in galaxies might have happened more slowly or unevenly than we currently think. Dust is crucial for planet formation, so this could mean that the conditions for forming rocky planets like Earth took longer to emerge. The entire narrative of how and when planets formed in the universe might be tied to the frequency of dust-free supernovae in the cosmos' youth. We can also speculate about how dust-free supernovae could affect the search for life beyond Earth. Dust-rich regions tend to have more molecular complexity, creating the chemical precursors to life. Dust-free regions might be chemically simpler or less hospitable to life's building blocks. So, knowing where dust-free explosions happen could help identify cosmic neighborhoods more or less likely to harbor life. There's also the matter of detecting these events with new technology. The next generation of telescopes, like the James Webb Space Telescope, JWST, and the Vera Rubin Observatory, will be able to spot faint, fast, and unusual transients better than ever before. They might discover many more dust-free supernovae, revealing patterns and populations that reshape our understanding of star death and cosmic dust production. One challenge remains. Because dust-free supernovae are faint and fade quickly, astronomers must catch them almost immediately after the explosion. This means wide-field, fast-response surveys are key. The more eyes scanning the sky, the more chances we have to spot these fleeting events and study their unique fingerprints. And studying them could help solve long-standing puzzles about supernova diversity. Astronomers have long struggled to explain why supernovae vary so much in brightness, duration, and spectral features. Dust-free explosions offer a new piece of the puzzle, showing how differences in the progenitor star's structure and environment produce radically different outcomes. There's also a social angle here. Dust-free supernovae remind us that the universe is full of surprises, constantly challenging what we think we know. As technology advances, we peel back layers of cosmic mystery, often finding more questions than answers. But that's the beauty of science, it never stops. These explosions offer a vivid example of how tiny details, like the presence or absence of dust, can ripple out and affect everything from the formation of planets to the detection of gravitational waves. It's a humbling reminder that the universe is interconnected in ways we are only beginning to understand. The implications of dust-free supernovae stretch far beyond what we've touched on. For example, when we consider the chemical makeup of galaxies, the lack of dust from certain supernovae could shift the entire balance of elements available for new stars and planets. Normally, dust grains are a fundamental ingredient in forming complex molecules. These tiny particles act as surfaces where atoms can meet, stick, and create molecules like water, carbon monoxide, or even organic compounds. Without dust, this molecular chemistry slows down or changes course dramatically. Think about a galaxy as a giant kitchen. Dust grains are the cooking utensils. Without them, it's much harder to prepare the recipes that lead to star and planet formation. Dust-free supernovae can be seen as events that remove some of these utensils from the kitchen, changing the entire cooking process of the galaxy. This might lead to slower star formation rates or less diversity in the types of stars and planets that form. We also need to consider the role of dust in shielding molecules and forming icy mantles around grains in cold molecular clouds. Dust not only helps molecules stick together but also protects fragile molecules from destructive ultraviolet radiation. In regions affected by dust-free supernovae, this protective effect could be diminished. This means molecular clouds exposed to such explosions might be more prone to molecule breakdown, affecting the chemical complexity necessary for building prebiotic molecules. Another point is how dust-free supernovae influence the interstellar medium's physical structure. Dust particles help regulate the temperature and pressure of the gas clouds and galaxies by absorbing starlight and re-radiating it in infrared. Without dust, these clouds can heat up differently and might not collapse to form stars as easily. So dust-free supernovae indirectly impact the physical conditions for star formation, possibly leading to regions with fewer or different types of stars. Let's switch gears and talk about how astronomers detect these dust-free supernovae. The usual way is through their light curves and spectra. A light curve is basically a graph of brightness over time, and spectra show which wavelengths of light the supernova emits. Dust-free supernovae tend to have shorter, sharper light curves, and their spectra often lack the absorption features caused by dust. These clues help scientists identify them, even though the events themselves might be faint or hard to catch early on. What's cool is that these detections require a blend of technology and timing. Modern sky surveys scan huge parts of the sky frequently to catch transient events like supernovae quickly. Once a potential supernova is spotted, astronomers rush to gather as much data as possible before the event fades away. It's like catching a lightning strike on film. Dust-free supernovae make this chase even more urgent because their signals are less obvious and fade faster. Another subtle but important detail is that dust-free supernovae could explain some missing mass problems in galaxies. When astronomers account for all the mass in stars, gas, dust, and dark matter, sometimes there are discrepancies. If some supernovae explode without producing dust, they could be ejecting material into intergalactic space in ways we don't fully understand. This mass might not be detected easily, hiding in forms or locations we haven't considered. On a cosmic scale, dust-free supernovae could also influence the evolution of galaxy clusters. Galaxy clusters are large groups of galaxies bound by gravity, surrounded by a hot, X-ray-emitting gas. Dust-free supernovae in cluster galaxies might release energy and material differently, affecting the temperature and chemical makeup of this hot gas. This could influence how galaxies and clusters interact and evolve over billions of years. Switching to a theoretical perspective, dust-free supernovae push the boundaries of how we model stellar death. Standard models assume a lot of dust and heavy element production. Incorporating dust-free explosions requires refining these models to include new variables like mass loss rates, binary star interactions, and magnetic field dynamics. These refinements help improve simulations that predict how galaxies and stars evolve over time. Some astrophysicists are also investigating how dust-free supernovae might connect to peculiar supernova types called Type IB and IC. These types lack hydrogen and sometimes helium lines in their spectra, suggesting their progenitor stars lost outer layers. Dust-free supernovae could be the explosions of these stripped stars. Understanding this connection might clarify the complex taxonomy of supernovae and the final fates of massive stars. In terms of cosmic recycling, dust-free supernovae might slow down the enrichment process of galaxies. Dust and heavy elements from supernovae seed the next generation of stars, making planets, and potentially life, possible. If dust-free explosions dominate certain epochs or regions, those areas might remain chemically primitive longer. This could mean pockets of the universe where the building blocks of life are delayed, leading to a patchy cosmic landscape of habitable zones. We can also think about the impact on cosmic reionization, a major phase in the early universe when the first stars and galaxies ionized the surrounding hydrogen gas. Dust affects how radiation propagates through space. Dust-free supernovae could allow ultraviolet light to travel farther, accelerating reionization in some regions. This would change the timeline and pattern of how the universe transitioned from darkness to light in its first billion years. Looking ahead, researchers are excited about how next-generation instruments might detect signatures of dust-free supernovae in distant galaxies. These detections could be indirect, like finding unusual abundance ratios in old stars or spotting anomalies in the cosmic infrared background. Finding these clues would open a new chapter in understanding cosmic history and the variety of stellar deaths across time. From a philosophical angle, dust-free supernovae remind us that the universe is full of diversity and exceptions. They challenge our tendency to categorize phenomena in neat boxes. Instead, they show that nature often operates in gradients and mixtures, with many outcomes depending on tiny initial differences. Dust-free supernovae are not just an oddity, they are a vital piece in the cosmic puzzle. They influence galaxy evolution, star formation, cosmic chemistry, black hole formation, and even the conditions for life. The more we study them, the more we realize how interconnected everything in the universe is, from tiny dust grains to the largest cosmic structures. If we want to fully understand the universe's past, present, and future, dust-free supernovae are a chapter we cannot skip. They force us to rethink how stars live and die, how galaxies grow, and how the cosmos recycles itself endlessly. They are a reminder that the sky we see is the product of countless hidden stories, waiting to be uncovered. The story of dust-free supernovae isn't just about stars dying quietly. It's about how silence in space can sometimes be louder than explosions. In a universe where so much of what we observe comes from light bouncing off dust or being absorbed and re-emitted by it, the absence of dust is like a missing layer in a painting. It forces us to interpret the image differently. Dust doesn't just color light, it filters, bends, and even hides it. So when a supernova happens without leaving behind dust, it changes how we read the cosmic canvas. Now here's something a lot of people don't think about: how dust affects what we don't see. Dust in galaxies can block starlight and make entire regions look dimmer or redder than they really are. When supernovae don't contribute to that dust, it might leave parts of space more transparent than expected. This can make galaxies appear brighter or clearer in some wavelengths, and that changes the way astronomers measure things like galaxy mass, size, and star formation activity. Without taking dust-free supernovae into account, some of those measurements could be off. Another fascinating aspect is the potential link between dust-free supernovae and galactic winds. When massive stars explode, they send shockwaves through space that push gas and dust out of galaxies. These outflows, or winds, help shape the galaxy's future by either fueling or halting star formation. If a significant portion of those explosions don't carry dust, the winds might have different physical properties: lighter, faster, and more ionized. That could affect how quickly galaxies evolve and how much material they lose to intergalactic space. Speaking of material, we also have to look at the role of neutrinos. These ghostly particles are emitted in enormous quantities during a supernova, and they carry away a huge chunk of the energy. In dust-free supernovae, the energy that would normally go into forming dust might be redistributed, possibly leading to more intense neutrino emissions or affecting how the shockwave behaves. Scientists are still studying whether these explosions have different neutrino signatures, and if so, how we might use those to spot dust-free events in real time. And then there's the magnetic field angle. Massive stars often have powerful magnetic fields, especially as they reach the end of their lives. These fields can twist, compress, and accelerate particles during a supernova. If the explosion happens in a relatively clean environment, without dust to slow or scatter particles, the magnetic field effects could be even more pronounced. That might lead to different types of cosmic rays being generated, charged particles that travel across the galaxy and even reach Earth. In other words, dust-free supernovae might be contributing a unique flavor of cosmic radiation. Let's not forget how strange this all is from a historical standpoint. Supernovae were once thought to be simple: big star dies, big explosion, lots of light, lots of dust. That model held for decades. But every time astronomers pointed better telescopes at the sky, they started to notice outliers, events that didn't match the mold. Some exploded faster, some dimmed too quickly, others didn't leave enough debris. At first, they were seen as oddities. Now we realize they might not be rare at all, we just didn't know how to see them. The history of dust-free supernovae is the story of science learning to pay attention to what's not there. And this brings us to early galaxies, the first ones that formed after the Big Bang. They were made of almost nothing but hydrogen and helium, with no heavy elements, no carbon, and no dust. The first stars that exploded in those galaxies couldn't have created much dust because the elements needed to form it weren't there yet. So in a way, dust-free supernovae might not be strange, they might actually be original. They could represent the universe's first default setting, and only later did stars become dusty. In fact, studying dust-free supernovae could give us a time machine. By understanding how they work and what they look like, we can better spot similar events in ancient galaxies billions of light years away. Those distant explosions help us trace the universe's chemical evolution, from a place of simple atoms to one filled with planets, people, and complexity. The absence of dust isn't just a mystery, it's a clue to how everything began. There's even a potential link to dark matter research. Dust complicates the light we see from galaxies, making it harder to model the gravitational pull of what's really there. If some galaxies have more dust-free supernovae, and thus less obscured light, they could serve as better laboratories for testing dark matter models. Cleaning up the picture might help reveal the invisible scaffolding that holds galaxies together. And as we explore all of this, we can't ignore how future technology will play a role. Telescopes like the James Webb Space Telescope, along with upcoming missions like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, will offer sharper vision into dusty and dust-free regions alike. They'll help us detect subtle differences in light curves, in chemical signatures, and maybe even spot the moment when a star fails to create dust. These instruments might show us how common these events really are and how deeply they've shaped the universe. Interestingly, dust-free supernovae might also help us understand why some stars just disappear. Astronomers have seen giant stars in distant galaxies vanish without a visible supernova. One theory is that these stars collapsed straight into black holes, quietly. But another theory suggests some of these might have been dust-free supernovae so clean, so fast, and so dim in the dust spectrum that we simply didn't notice them. If that's true, then dust-free supernovae might be masquerading as missing stars. The deeper we look, the more it becomes clear that the universe isn't just filled with noise and explosions, it's also filled with silence and missing pieces. Dust-free supernovae are one of those silences. They're like whispers in a shouting crowd. Most telescopes were designed to hear the shouts, not the whispers. But now, scientists are tuning their instruments and their theories to pick up on these quiet but powerful cosmic events. And if you think about it, this silence is poetic. Stars live for millions or billions of years, burning, fusing, building the elements that make us. Then, in death, some don't scream. They don't light up with all the fury we expect. They go out cleanly, subtly, without leaving much behind. But in that quiet end, they still shape galaxies, shift cosmic chemistry, and leave echoes that last for eternity. So next time you look at the night sky, think about what's not there. Think about the explosions that didn't leave dust, the stars that died without drama, the mysteries wrapped not in light, but in its absence. Because sometimes, the biggest discoveries don't come from what we see, but from what we almost missed. The idea that a star can explode and leave behind almost nothing but energy, no dust, no thick clouds of debris, is like hearing thunder with no storm in sight. It defies what we expect, and that's why it's so important. These dust-free supernovae are challenging some of our oldest assumptions about what stars do in their final moments. Not only are they helping us see the past differently, but they're also forcing us to question how complete our understanding of stellar death really is. If dust-free events are more common than we thought, it means we've been painting the story of the cosmos with a missing brushstroke. Now, let's talk about the elements themselves. In most supernovae, dust forms because the explosion throws out heavy elements, carbon, silicon, oxygen, iron, and they clump together in space to make microscopic grains. These grains eventually join larger clouds, helping form planets, comets, and new stars. But in a dust-free supernova, either those elements aren't produced in the same way, or they don't have time to condense before being blown apart or vaporized. That suggests a totally different chemistry at play, and that could change what we think we know about the chemical enrichment of galaxies. What's even weirder is how this affects the recycling system of the universe. Normally, a supernova is part of a feedback loop. A star lives, explodes, creates dust, and that dust helps birth new stars. But a dust-free supernova skips part of that cycle. It injects energy without giving back the raw materials needed for the next generation. It's like taking a piece of wood from a fire without replacing it. Over time, this could lead to regions of space where star formation stalls or changes direction entirely. And the environments where dust-free supernovae happen are also worth thinking about. They're more likely to occur in places that are already clean, galaxies with low metallicity, or low concentrations of heavy elements. These are usually older galaxies, or ones far from the bustling centers where stars are packed closely together. That means dust-free explosions might be leaving their mark on some of the quietest, loneliest corners of the cosmos, places that we don't look at very often, but which may hold vital clues to the early universe. We also can't ignore how these explosions could be influencing the intergalactic medium, the thin gas that floats between galaxies. Every time a star explodes, it throws material into this space. But if it's a dust-free explosion, that material is different, more gas, less solid matter. Over millions of years, that could make a difference in how easily light travels across the universe. It might even affect the large-scale structure of the cosmos in ways we don't fully understand yet. And then there's the light itself. The way a dust-free supernova looks is subtly different. It might rise and fade faster, or emit more ultraviolet or X-ray light than a normal supernova. This can trick our telescopes into misclassifying them. We might think we're seeing a different kind of stellar event, a gamma-ray burst, a failed supernova, or even a star that didn't explode at all, when really it's a dust-free event that just looks unusual. This means our catalogs of stellar explosions might be filled with hidden examples we never noticed. Think about what that means for our understanding of cosmic history. If we've been undercounting or misclassifying a whole category of supernovae, our models of galaxy growth, star formation, and even cosmic expansion might be skewed. The implications ripple out in every direction. We could be wrong about how fast certain galaxies grew, or how much energy is floating around the universe. And all of that just because of a lack of dust. Now let's get into the topic of black holes. There's growing evidence that dust-free supernovae might be linked to the formation of some black holes. In certain cases, the explosion is so efficient and clean that very little material is left behind. That could allow the core of the star to collapse straight into a black hole, without a lot of messy fallback or debris. It's a more surgical collapse, quiet, direct, and final. This might explain why some black holes appear in places where we didn't see a big explosion before. And this goes even further. Some researchers are exploring whether certain gravitational wave events, ripples in space-time caused by massive collisions, might actually be linked to dust-free stellar collapses. If two stars explode without leaving dust, then later merge as black holes or neutron stars, their original explosions might have gone unnoticed. We'd only catch the final collision, not the beginning of the story. That adds another layer to how dust, or the lack of it, hides or reveals the truth in space. Let's now consider the role of computer simulations. The physics of dust-free supernovae is so complex that scientists have to model it using enormous simulations that track everything from fluid dynamics to radiation flow. These models are helping us understand how a star could explode without forming dust, and what kind of conditions would lead to that. Some early results suggest that if the outer layers of a star are stripped away by a companion star, or by previous eruptions, then the explosion might not produce the right environment for dust to form. That's another clue. The absence of dust might point to a violent pre-supernova life. It's also worth asking how common these events really are. Early studies thought dust-free supernovae were extremely rare. But more recent surveys, using instruments that look in the infrared and ultraviolet, are starting to suggest otherwise. Some astronomers believe that up to 20% of all core collapse supernovae might be dust-free to some degree. That's not just a statistical fluke. That's a whole new branch of the supernova family tree. And if that's true, we've been missing out on one of the most important parts of the stellar life cycle. Let's bring it back to Earth for a second. Our own sun won't go supernova, it's too small, but many stars that did go supernova in the past helped create the dust that became our planet. If too many of them had been dust-free, maybe there wouldn't have been enough solid material to build Earth at all. That's a strange thought. The presence or absence of dust in ancient stellar explosions may have influenced whether planets like ours could even exist. And on a philosophical level, dust-free supernovae remind us that absence is just as meaningful as presence. In a universe so focused on energy, brightness, and matter, sometimes it's the empty spaces, the things that don't happen, that tell the bigger story. Dust-free supernovae are the blank pages in the universe's diary. They're hard to read, but once we start decoding them, they could rewrite the story we thought we knew. And we're just getting started. We've only scratched the surface of what these quiet, clean explosions could teach us. There's still so much we don't understand about their frequency, their exact chemical profiles, their relationship to black holes, and their long-term impact on galactic evolution. Every observation adds a piece to the puzzle, but there are still more questions than answers. And that's the best part. Because in science, mystery isn't a wall, it's a doorway. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.